All right.
Okay. Hello, everybody. Good evening. Thank you very much for coming to our June the 12th Friends of the DAO Summer Star Party. We are going to be having a pretty full evening tonight, and we welcome people both on Zoom and on Facebook, or sorry, on YouTube today on our YouTube channel. So the first thing that I would like to do is to take a moment to acknowledge that we are on the traditional territories of the Coast Salish and Lekwungen speaking people, who are the custodians of these lands and waters. The area has long been the gathering place of the Songhees, the Esquimalt, and Wasanich nations long before the arrival of Europeans. We are grateful to have the opportunity to live, work, collaborate, and learn here, and we respect the continued connections with the past, present, and future in the ongoing relationships with Indigenous and other peoples within the British Columbia community. We invite all attendees tonight to reflect on the land upon which you are located and the relationships you have to the communities that you have inhabited and continue to inhabit. Thank you. I'm going to just do a little bit of a schedule tonight to let everybody know what's going on and introduce some of the people that are going to be coming to you. So the first thing we have is Amy Archer is going to be doing our announcements tonight. She is our host on YouTube, and she is also going to be the host for Ask an Astronomer. Amy is our treasurer for the FDAO. Calvin, can you highlight Amy so that we can see what she looks like? There she is. There you go. And she has been working with us now for how many years, Amy? Is it like 4, 5?
I think it's 5.
I think it's kind of 5 years. That's right. Yeah. Looks after the gift shop. Does all the work there and keeps us all going and pays people that need to be paid and all of that kind of thing. She's awesome. Thank you, Amy. So after the announcements, we're going to be having our guest speaker. I will be introducing James Defrancesco a little bit later, before he gives us our presentation. And then after that, with the questions and discussion, we're going to be having Patricia Gilbert Sturm and I will be giving a little bit of a presentation together on the summer solstice, and we're going to be talking a little bit about what happens on the 21st of June. And then Aaron Bannister is going to be coming in on to do some of the work and show us some of the images from the annular eclipse that was just happened last Thursday, and he's got some lovely photographs to show us from all over the place. Then we're doing an Ask an Astronomer tonight with 2 people. The first one is Reg Dunkley, and Reg is going to be coming in. He is the past president of the Royal Astronomical Society. There's Reg. Hi, Reg. And he has he's all smiles now because he's the past president. He's not the president right now. Yeah. and Reg is our resident meteorologist. And he takes full accolades for great, beautiful weather for anything that happens in the sky for nighttime viewing, but totally takes absolutely no blame for things like tonight's sky. So, just it's one or the other. And then the other person that we have is Scott Wilkinson. There's Scott. Hi, Scott. And comes from UVic. Scott has just received his Bachelor of Science with distinction, and he is going to be working with Sarah Ellison on some galaxy evolution work for the next little while, doing his going through for his Masters of Science. And he has been really doing a lot of work with the open houses with UVic, and we're really happy to have him here tonight, doing not only the Ask an Astronomer with Reg, but he's also going to be doing some of the narration with the EAA a little bit later on. So thanks for coming and helping us out, Scott. Then David, we're going to turn it over to David Lee. David is going to be doing What's Up in the Sky. There's David. Hi, David. And then then kind of gradually kind of shifting right into the EAA. Now, if it was really nice tonight, he and his confreres with the electronically assisted astronomy group would be having all their telescopes up, but both Dave Payne says nope, they haven't even got a telescope up tonight. There's just no way that there's going to be anything. So they've got a whole program for us of images that have already been downloaded and are ready to go. So he's going to be working on that. So that is what we're going to be doing for the evening. And I'm now going to turn it over to Amy, who's going to give us a few announcements before we start.
Hi. I'm going to go through just a couple housekeeping announcements. So one of the things is just, I think, in terms of your videos, if they're on, we are going to, you might find that we turn them off. But don't worry if they stay on as well. You won't be seen on YouTube if that's not what your desire is, if you're joining us on Zoom. As far as the chat box goes, we're hoping that you will use the chat box for your questions. So on both YouTube and on Zoom, if you have any questions, please put them in the chat box. And we might hold some of the questions for the Ask an Astronomer section. So we will get to them. And then I wanted to just say, if you haven't come to us via the centeroftheuniverse.org website, we would really love to know how you found out about us. So if you could just put quickly in the chat on, again, either YouTube or on Zoom, just where you heard about this star party, that would be so helpful for us. And the other wonderful thing about the centeroftheuniverse.org website is that you can find out how to become a member if you are not one now. You can also see how you can make donations, and your donations go a long way. I think Lori told you I deal with the numbers, so have to say, you know, your donations really go a long way towards science outreach and you know, the center. But right now we have managed to continue our school programs even through the pandemic. So you know, there's still a lot of really good things happening in the community, and we always appreciate those donations. I'm also going to say that on that website, you can also see a link to our store. And so the store that people are used to visiting when they are on the Hill, we're still dropping packages off. If you're local, I will drop it off right into your hand. And if you are remote anywhere in the world, we can get you a package. So check out our store. And, you know, I always just like to mention to people that there is a board of, I believe it's 9 of us, that do a little happy dance with every order, because that means that a school program can run, or our staff, you know, are going to be happy because they keep getting paid. So we really appreciate that support. Of course, you are on this star party, so you will want to earmark that the next star party is happening on June 26th. And we're going to have Jenny Atwood and Scott Roberts from the NRC speaking about, if you're local to Victoria, you may have noticed on the Hill, there is a new green, kind of not quite tree color green, sticking out just below the dome. And so they're going to talk to us a bit about what that green building is about and what's happening in there. And lastly, I will just ask and remind you that you can follow us on YouTube. And if you click the notification bell, you will know every time we have any kind of offering. And then on Instagram and Facebook as well for all of the latest news on what's happening in the FDAO. So I hope you enjoy the star party tonight.
Thank you. Thanks, Amy. And there we go. Am I unmuted there, Calvin? Am I okay?
Yeah, you're good now.
Okay. And so what we're going to do now is to go into our guest presentation. And I would like to introduce you to James Defrancesco. And James was born in Southern Ontario, raised in Southern Ontario, obtained his PhD in astronomy at the University of Texas in Austin in 1997, researching circumstellar environments of young stellar objects. This research consisted of far infrared mapping of the natal envelopes of intermediate mass objects and millimeter interferometry of their accretion disks. Now, I don't know all of that. I didn't completely get everything, but that's okay. I still love to listen to him. It's no problem. He spent 3 years with the Harvard Smithsonian Center for Astrophysics in Cambridge, Massachusetts. And then he went to the University of California in Berkeley and joined the Millimeter Astronomy Group here in Victoria at the National Research Council Herzberg Astronomy and Astrophysics in 2002. And James has been the director of the DAO since 2018. Now, earlier in the year, James gave us a presentation on searching for life within our galaxy, and within our solar system, and what we would be able to do so that we would be able to look at different planets and think, okay, is there life on some of the other planets? What's happening in part of our solar system? So today he's going to be talking to us about things that are further afield, and he's gone into the galaxy, far from our kind of into the galaxy and even beyond, to see whether or not he can look for searches of life in some form out there. So I'm going to turn it over to James. Thank you again for coming back, James. We really appreciate you doing this, and we look forward to your presentation.
Thank you, Lori, for that very warm introduction. It's a pleasure to be back here speaking to you today. I had a really good time talking to you, almost 6 months ago. It's hard to believe. Those of you who saw my first talk probably have recognized that I don't have my beard anymore, which is probably a good thing. But it's really great to be able to continue talking about this subject because I find it very, very interesting. So I'm going to try to share my screen. Let me know if this works, please. Okay, can everyone see my slide? Yeah, okay, thanks, Lori. Great. Okay, so this topic is, I think, a really fascinating topic, and I'm really happy that you've decided to join me tonight on your Saturday night to learn a little bit more about this, this topic. Now, it is not a topic that I myself research, but my own research is actually more about how stars themselves form. But as an astronomer, I find that when people find out I'm an astronomer, one of the top 3 questions that I get asked is, what do I think about aliens? What do I think about the possibility of there being life elsewhere? So I realized that it is an extremely interesting and important topic to a lot of people. And so I find it very interesting too. And so I have made myself very aware of the circumstances of which people are actually spending their careers studying the possibility of there being extraterrestrial life in the universe. Now, as you can see from this title slide, a lot of people are interested in the idea of aliens. It certainly permeates our popular culture. And I think that shows that there is a tremendous amount of interest amongst people about the possibility of there being aliens elsewhere. So in this presentation, I want to describe basically why we would want to look for extraterrestrial intelligence, and also how people are actually going to do that. And then at the end, we'll discuss the prospects of whether or not it will be possible to see these or to contact these aliens in the foreseeable future. So to begin, let's start with the Earth. So why do we care about extraterrestrial intelligence at all? Now, when we get to look at the Earth itself, sort of suspended in the blackness of space all on its own, you have to come to terms with the fact that this is the only place in the universe that we know of where life exists. Now, life is very plentiful here, and the Earth is a fantastic place, but it really is the only place that we know where it exists. And on top of that, we, as a species, humanity, are the only intelligent species that we know of as well. So we are, I think, driven to try to find out more about the possibility of there being not only life elsewhere in the universe, but intelligent life as well. Now, in my previous presentation, way back in the end of December, I took us on a tour of the solar system to try to understand if there were places in the solar system where extraterrestrial life could be found. And I spotlighted 4 particular objects, planets and moons in the solar system, where it seemed that the conditions may be ripe for life to have arisen. But what we found, though, was that there absolutely is no indication of there being any intelligent life out there in our solar system. What we find instead are mostly worlds where the promise of life may exist, but if that life exists, it must be extremely basic. Now, we have spent about 40 years trying to explore these various worlds more and more, and we're going to continue doing so. So hopefully the idea that life may exist on these planets or not will be answered relatively soon. But for now, we have to at least accept the fact that there are no intelligent civilizations on any other planet in the solar system except our own. And I will say, of course, that Venus is a very unlikely place where life may exist, because it seems that the data, which was reported last fall, that suggested perhaps biological activity in the clouds of Venus turned out to be flawed. And so it really isn't a candidate for which we can expect life may persist on that planet. So, what we think about, though, in our solar system is that maybe there are places where microbial life has occurred, these microscopic animals, of which there are many plentiful varieties on the Earth. These very simple life forms are, in fact, still the dominant form of life on the Earth in terms of number. I mean, the microbes certainly were the only form of life on the Earth for maybe 1 billion years when life arose. And it wasn't only until after that time that more complicated and complex forms of life arose. But microbes are very fascinating, and it would be actually really amazing to be able to detect or find the presence of microbes on places beyond the Earth, because it would indicate that life could arise elsewhere, which is a major thing that people would like to know. But the problem with microbes, fascinating though they are, is that they're extremely hard to have a conversation with. I mean, I would even go so far as to say that, have you ever had a conversation with a microbe? It's actually pretty boring. You can talk at them all you want, but you're never really going to get an answer that you'll find very compelling. So not to say that microbes are boring, but just to say that you're not going to have a very interesting conversation with them at all. Instead, we have to leave the solar system. We have to venture out into the galaxy and find other locations where life might exist and intelligent life might exist. And we would actually like to have situations where we can actually talk to perhaps other civilizations and find out more about what it's like to be in their parts of the galaxy. So, I mean, this sort of conversation that I'm showing here is, again, meant to be something of a joke, but more seriously, there's actually some very interesting and good reasons for why we would want to contact an alien civilization. And part of it comes for what we understand about what intelligence is and what it does. So when we think about intelligence, human intelligence, that is, I think that there are 4 themes that comprise human intelligence. I think that for humans to be intelligent, we have to do 4 things in order to be able to produce the kinds of things that intelligence produces. So basically, we have to remember stuff. We have to have some capacity for remembering what we have done before, because we can build on that to provide understanding. That is, we'll be able to use our brains to figure out what's going on around us, at least to use things around us. And then on top of that, we use our intelligence to synthesize things, to create things. We as intelligent beings, we actually produce things that don't exist in nature itself. And then we actually communicate these things. So these things that I'm talking about are, of course, ideas. They're concepts. They're things that we actually produce as an intelligent species. And it's these ideas, this information that we produce that I think is the real treasure trove that we could unlock if we were able to contact an alien civilization. And I mean, just think about it. All of the incredible things that humans have done in the last 7,000 years of our civilization. I mean, think about all of the music and the science and the literature, all of the fashion and the creativity that we have done, the dance, the arts, the singing, all of that stuff that we have done is impressive. It is a result of our intelligence. But we have only been really members of the intelligent community, if you will, a civilized community for only 7,000 years. And really, as we will see, an intelligent civilization elsewhere in the galaxy may not be necessarily that young at all. And in fact, it could be far, far older and have, by orders of magnitude, we're talking maybe hundreds or thousands of times older than our own civilization. And I think to these civilizations, as impressive as our achievements are, we would be as children, in the sense that basically our own things that we have created are still on a very rudimentary level. But I think also as children, perhaps they would also speak to us as perhaps people that would want to learn, that we would be able to learn more about the things that they themselves have come to understand in the long years of their own civilization. And that's just only one civilization as well. I mean, the galaxy could be filled with hundreds or thousands of civilizations out there, each one with a rich and impressive culture that they have developed over perhaps millennia or more. And tapping into that incredible amount of information and knowledge out there, I think would be a tremendous watershed moment for our species. And so I think that alone is the real driving force to why we would want to spend time and energy looking for these other intelligent civilizations elsewhere in the galaxy. They can teach us so much if we are only able to tap into them. Of course, the trick is we have to actually make that contact, and that is not an easy thing at all. And so one thing that we would like to know is just how many interstellar civilizations could possibly be out there. And I'm going to restrict this conversation only to really within our own galaxy, because other galaxies, though they may have life that has risen there as well, even intelligent life, they're just so far away that the prospects of communication, I think, are really quite remote. So when we try to figure out how many interstellar civilizations could be out there, we can be aided by this very famous equation that was developed almost 60 years ago by a man named Frank Drake. It's called the Drake equation. He came up with it. Now, Frank Drake was an interesting character because he was one of the first people to actually point a radio telescope towards a star to try to see if there was some alien civilization out there that was trying to communicate with us. And now, as a result of his pioneering actions, he prepared a conference. I think it was in 1960 or so. And he was preparing a conference. He began to think about all of these different factors that needed to be understood for them to know just how many possible civilizations could be out there. And then he realized that all he needed to do was multiply all of these different factors, and he would actually come up with a number, an estimate. Now, the Drake equation, which I'll explain these factors in a minute, has actually been a little bit derided because some people think it's a bit unscientific because some of these factors are just so hard to determine that it's almost meaningless. But I think that's actually the wrong attitude to take. Instead, we should treat it more as a heuristic device, a way of framing the conversation and breaking down the question into individual elements that we could perhaps address. Now, what are those factors? What are those elements? So if we break down the Drake equation into its factors, the first variable, well, n is the number of communicative civilizations that are out there in the galaxy at the moment. R, the first factor, is the average rate of star formation in the galaxy. How many stars are being produced in the galaxy in a given year? F sub S is the fraction of stars that have planetary systems. Not every star should, or perhaps has planets, but some fraction probably does. And so what is that fraction? What is the number, or N of E is the number of planets around these stars within what we would call an ecoshell or a habitable zone. This is a range of distances from the star where perhaps liquid water might be possible given the heating done by the star. Now, F of L is actually the fraction of those planets where life develops, and F of I is the fraction of those species that that develop intelligence. And F sub C is the fraction of those that actually are able to develop communications technology, ways in which they could communicate with others in the galaxy. And the big factor is that at the end is L, which is the lifetime of the communicative phase of a civilization. Now, the interesting thing about the Drake equation is that as you go from the left to the right, these factors actually become more and more uncertain. We can use astronomy, for example, to put some really solid constraints on these first few factors. But as we go further down over to the right, these factors are harder and harder to estimate because we simply just don't know what fraction of planets where does life develop? What fraction develops intelligence? How many of those actually are able to develop technology? We just don't know. I mean, we're the only species we know that has actually managed to go through all of these steps on our own. But nevertheless, it's a good framing device because we can then, using some estimates, some guesses, we can actually get some pretty interesting results that at least limit the number of communicative civilizations out there. And you can do this, well, let me just say again, that astronomy has helped us at least put some answers now to some of these factors. One of the things that we didn't know when Frank Drake actually produced this equation 60 years ago was actually whether there were even any other planets around any other stars. And thankfully, due to efforts like that done of my colleague Christian Marois at the Observatory, we actually have a much better understanding that planets do exist around other stars. And that's great because with statistics, we can actually begin to plug in numbers of real value into the Drake equation when that wasn't possible before. I mean, here is a movie showing actually planets that have been imaged towards the star HR 8799. And you can see how these planets are circling, orbiting around the star, whose light has been very cleverly blocked through a very interesting means, just so the brightness of the planets themselves could be revealed. So it's images like these and other data that really tell us how many planets could be out there, and the number of planets actually appear to be quite startlingly high. And that's thanks to missions such as the NASA's Kepler telescope, which maybe 10 years or so ago was able to look at a large number of stars in the galaxy at once. And by staring at a particular patch of the sky where there were a lot of stars, it could look and see where were stars dipped in their light as a planet around them passed in front of it. And monitoring those dips and then seeing those dips occur year after year allowed the Kepler team to build up a fairly impressive amount of exoplanets that were out there, planets around extrasolar systems. Now, Kepler has actually discovered thousands of planets in just this one small patch of the galaxy. And that's only the fraction of stars where planets were able to pass in front of the disk of the star and dim its light. Now, by doing some statistics, you can actually correct for those biases. And from that, you can actually come up with a number of really how many planets there are around stars in the galaxy. And so far our best statistics are there about 1.6 planets per star in the galaxy. What that means is that there are some stars that don't have any planets, and then there are some stars that have lots of planets. But on average, it comes out to be about 1.6 planets per star. And given the sheer number of stars in the galaxy, this means, because that number is greater than 1, that there are actually more planets in the galaxy than there are stars. We're talking about 160 billion planets out there, which is a staggering amount of real estate for life to have developed, let alone intelligent life. So that is very encouraging, that there does seem to be a lot of planets out there for life to have arisen. Now, going further, Kepler was able to actually put some limits on how many of those planets actually appear to be in the so-called habitable zone, this range where liquid water could exist given the distance of the planet from the star. That is, the star would be able to warm water on the surface of a planet so that it would actually be liquid. And what we see is that, for example, in our solar system, Earth sits smack dab in the middle of the habitable zone. Venus is just a little bit on the interior. Mars may be on a little bit on the edge of it. But nevertheless, there are other planetary systems where there are several planets within the habitable zone of their particular star. One is this TRAPPIST-1 system, which Kepler didn't discover, but it was another form of survey which was able to detect planets. And in this system, which consists of 7 planets, there are 3 that are arguably in this habitable zone. And it's these kinds of observations that have shown that actually about a quarter of the planets out there, maybe 40 billion planets, are actually within this habitable zone. 40 billion potentially habitable Earth-sized planets out there, which is an astoundingly enormous number for us to begin to look at when we are thinking about the idea of intelligent life elsewhere in the universe. So we can actually use a simple spreadsheet to play around with the various factors in this Drake equation and come up with some what you would call very pessimistic or very optimistic cases for the possibility of there being extraterrestrial intelligence elsewhere in the galaxy. Now using the Kepler and other planetary system survey results, we can actually plug in realistic numbers for these first 3 factors. I mean, the average rate of suitable star formation in the galaxy is probably roughly around 3 stars a year, though that could be maybe as low as lower by a factor of 3 or higher by a factor of 3. We're beginning to nail that down, at least within an order of magnitude. And combined, these next 2 factors really are the fraction that are able to produce habitable planets per star, basically a quarter. And then we get into the very uncertain parts of the Drake equation. And pessimistically, we could say, okay, maybe 20% of those habitable planets have life arise on them, and maybe 5% of those planets are those where intelligence evolves. And then maybe a quarter of those are then capable of interstellar communication at this time. And then maybe the lifetime of a detectable civilization or its communicative phase is relatively short, or about 500 years. And that, putting all those numbers together, you actually get a number that's very close to 1, which basically would mean us. We are the only intelligent species in the galaxy. I hope that's not the case, but these numbers could suggest it, especially if that L number, the lifetime of a communicative civilization, is particularly low. Now, we could be more optimistic, and we can increase those values. We can say, okay, maybe the fraction of these habitable planets where life arises is actually higher. Maybe it's 80%, and maybe 2/3 of those is where intelligence evolves. And maybe once you get intelligence, eventually you do figure out how to communicate across interstellar space. And maybe the length of years of which a civilization exists is much, much longer. Maybe it's 50,000 years. In fact, it could actually be longer. Maybe it's 100,000, maybe it's 1,000,000 years, who knows? But at least at this relatively conservative level, we can find that we can actually surmise that we get about 20,000 broadcasting or communicative civilizations in the galaxy, which is a pretty huge number out there at any given time. Okay, so how can we communicate with all of these possible civilizations out there? Well, it's a very, very good question. But to understand the limits that we have in this possibility, we really have to understand some very hard truths about the scale of the galaxy and of the limits on physics as well. Namely, we have to understand, for example, the speed of light. So the speed of light is actually the fastest possible speed in the universe. And thanks to Einstein, we know that nothing can go faster than that. In fact, as you get closer to the speed of light, it becomes increasingly harder. In fact, you get to a point where you just cannot pass beyond the speed of light. It's built into the fabric of the universe. Now that speed is very, very fast. It's 299,702, 458 meters per second, which is crazy fast. But it's not infinite. And on astronomical scales, which are very, very large, it can still be a very relatively low number. And just to give you some examples, a beam of light would take only about 1 second to reach the moon from the Earth. That's how far away the moon is from the Earth. 1 second doesn't sound so bad, does it? But it actually takes about 8 minutes for light to travel from the sun to the Earth. So when we see the sun in the sky, we're actually seeing it 8 minutes ago when that light actually left the surface of the sun. Now, consequently, if we imagine the scale of the solar system, it actually takes a beam of light 5.5 hours to go all the way from the sun to Pluto, which is on the edge of our solar system. Now, that's our solar system, but the scale between stars is far, far, far larger. And it would take actually 4.3 years for a beam of light from the sun to get all the way to the closest star that we know, which is called Proxima Centauri. And in fact, that enormous distance is something that we can only are able to really best describe using a unit that is based on how fast light or how far light travels in a year. This unit is called a light year, and it's equal to just a little bit less than 10 trillion kilometers. So that's an enormous distance to travel in a year, but still, its space is even bigger than that. So, and that's just even to the next star. When we think about the Milky Way, which is not shown, this is a picture of another galaxy for just for as an illustration. The galaxy is itself gigantic. It is 100,000 light years across, and it is about 1,000 light years thick. It's basically like a disk, a big pizza. That's 100,000 light years across and about 1,000 light years thick. And in that volume, there are 100 billion stars. In fact, there may be even 1 trillion stars, but at best, we think it's about 100 billion stars at this time. And on top of that, the galaxy itself is very, very old. It is 10 billion years old. And that's twice the age of our sun. The sun is about 5 billion years old. The Earth is about 4.5 billion years old. And even in that time, the galaxy itself has only rotated about less than 50 times over its entire existence. That's because it takes the galaxy about 250 million years to rotate once. And over that time, you would expect it to maybe only have rotated about 40 times. And I only say that to put that into perspective. The galaxy is humongous, and it's also very old. So these actually put very strict limits on our ability to communicate with other alien intelligences, because the scale of the galaxy is so very large, and light, fast though it is very limited in its ability to go from one star to the other. So how would we actually do this? Well, we actually come up with some very interesting ways of communicating with extraterrestrial intelligences. And I'm going to go through them one by one. And I think the very interesting first method that has been done is an approach that I would call a message in a bottle approach. And this is actually putting something on a physical artifact and then throwing it out of the solar system. Now, this was done first by the Pioneer 10 and 11 probes, which were launched in the early 70s, basically almost 50 years ago. And affixed to them were this rather scandalous plaque that I am showing right here. Now, this plaque has a message on it, with the possibility that any alien species that discovers it might learn something about where this probe came from. And it's a lot of interesting things on here, and I'll try to briefly explain what some of them are. What's shown here at the top, these circles, they basically represent the transition that hydrogen makes from one state to another when it actually the electron in the orbit around the nucleus flips its spin and produces a very dominant line of emission, at a specific frequency of about 1.4 gigahertz that all the hydrogen in the galaxy actually produces. And so it's a very common touchstone in terms of a frequency that everyone should be able to understand. Now, obviously, you can see the man and the woman here, which are, of course, naked to try to display our complete anatomy. And behind that, to scale, is the Pioneer 10 or 11 spacecraft itself in silhouette. Now, these radial lines are basically a way of describing where the source of the probe came from. And they show the directions to different pulsars in our galaxy, with the Earth at the center. The idea being that the various precise periods of those pulsars, which are rapidly rotating neutron stars, are indicated by these dashed lines. The idea being that maybe if some alien species were to know about these pulsars and know about their frequency, they could then identify it and then trace back to where the Earth is. And then, of course, here at the bottom, you see a schematic of the solar system, where the origin comes from the third planet, namely the Earth. Obviously, this was done a long time ago because Pluto is still indicated as a planet here. Oops. Okay, so this was only the first message that was tossed out of the solar system. Another probe, which was launched in the late 70s, so actually two probes, Voyager 1 and 2, also had a much more complicated and involved message affixed to it. Now, Voyager, like the Pioneer spacecraft, went out into the gas giants in the solar system and were the very first probes to image their surfaces. Voyager 2, in particular, went from Jupiter to Saturn to Uranus to Neptune and was able to produce incredible images of their surfaces that no one had ever seen before. But it did that by basically hopping from one planet to the other, as they were very beneficially lined up in the solar system at that time. And then after Neptune, it is continuing on out of the solar system. And with the possibility that perhaps some alien species might find it someday, actually the Voyager spacecraft were affixed with a record, which actually has a lot more information than the Pioneer 10 or 11 plaques. Like Pioneer 10 and 11, it actually has the image of the hydrogen transition, which produces that very specific burst of light at 1.4 gigahertz, so that the species could begin to understand what's going on. And it has that map showing where the Earth is amongst those pulsars. But it also has instructions about how to use the record. Now, both it and the Pioneer 10 and 11 message are actually gold-plated. They're meant to last a long time. And this particular record comes with a stylus with these instructions that actually allow the record to be played. And the contents of this record are actually pretty amazing. It contains greetings in 55 different languages and recordings of natural sounds. There are samples of music from Bach and Mozart and other classical composers, as well as more modern people like Chuck Berry and Blind Willie Johnson. as well as recordings of other music beyond North America as well. And encoded in it as well are 115 pictures of various scenes on Earth. And it's actually an amazing story about how these messages are actually decided and how they came to be. And I really strongly urge you to read up on it because it's a very fascinating story. How do you choose what to represent the Earth to an unknown cosmos? But you can actually go online and listen to some of the samples of these music yourself and judge for yourself if it is the right thing to have included. I think it's fantastic. Now, unfortunately, I have to tell you that it's very unlikely for an alien species to actually recover this physical artifact. The Voyager spacecraft are actually some of the fastest objects that have ever been created by humanity. And they're both going around 15 kilometers per second. So every second that I'm talking, they're getting 15 kilometers further and further away from us, which is an astonishing speed. But even at that incredibly high speed, it would take them about 86,000 years for them to even reach a distance equal to that of the nearest star, Proxima Centauri. And it's not even going in that direction. They're not even going in that direction. In fact, in 40,000 years, Voyager 2 will maybe pass within about 2 light years of the star Ross 248. And in 300,000 years, it will pass maybe between 4 light years or so of the star Sirius. So it's just these amazingly huge amounts of time that these fast objects would take that makes it extremely unlikely that any alien civilization in any of those stars would be able to recover it, let alone the fact that it's only one little tiny probe in a vast and empty universe. The chances of it being ever recovered are so low that it's something infinitesimally larger than zero. So, I mean, I don't want to be down on this because I think it's actually an incredibly moving and beautiful thing to have taken some sample of the Earth and cast it out into the cosmos. It's a wonderful, wonderful gesture that says to the universe for eons to come who we are and what we did. But I just think that it's very unlikely that these objects are ever going to be recovered and be the kinds of message that perhaps an alien civilization would like to receive. That said, I mean, there are possibilities of maybe having faster probes out there. And I just would like to turn your attention to this interesting possibility that has come up in the last few years. This is a project called Breakthrough Starshot. And the idea is actually to produce an even faster probe that will reach the nearest stars in a lot less time. The idea is to put a chip that is basically incredibly small and light and have it in the center of a huge solar sail, something that an array of lasers could point at. And then the light from the laser would push and accelerate that sail to an extremely high speed. It would have to be light for it to be able to be accelerated to such a high speed. And with this burst of light, the probe could be launched to an appreciable fraction of the speed of light, maybe about 20% of the speed of light or something. And with that, it could go winging across the space between the sun and maybe even the nearest star, like say Proxima Centauri. And in that time, it could then perhaps reach that within about 20 years or so, because 4 light years or so at 20% of the speed of light, you would get there in maybe about 20 years. And then with instruments on it, microscopic instruments, but instruments all the same, it could perhaps transmit those images back to the Earth and allow us to see what the planets around a nearby star system like Proxima b could see. And with this in mind, maybe such a probe could itself have a microscopic message on it as well that perhaps an alien species then could recover in a lot less time than perhaps the Voyager or the Pioneer messages will. So it's a very interesting idea, and we'll see if this actually comes to be. This is not a project that is going to happen. It's a project that is being studied right now using some seed money from a very ambitious and philanthropic man named Yuri Milner, who is putting out his own money to investigate these very interesting ideas. More on him in a second. Okay, so moving on, maybe what we could do instead of sending a physical object, we could actually broadcast a message. The advantage of this is that, well, one, it would actually go a lot faster than a physical object, because the light that would be broadcast, the radio waves that would be broadcast, would themselves actually go at the speed of light. Now those distances are still enormous, but still it would go as fast as anything can go. And it's this sort of thing that has been attempted in the past. For example, in the early 70s, the Arecibo radio observatory, which is shown here, was used as the emitter of a signal that was sent off to a globular cluster known as Messier 13. Messier 13 has maybe about 100,000 stars at it, so maybe the thinking was that this message could be sent out and a lot of stars would be able to receive it at once. So the message actually is very interesting. It was a series of signals that were sent in a burst. Maybe I think it only took about 5 minutes or so, where the various modulations of the signal could be interpreted as zeros and ones. Now, each digit is itself a bit, and it was important that perhaps an intelligent species might need some clue as to whether or not this was an actual message or not by the number of bits that were in the message. And the number of bits was actually 1,679, which is a number that perhaps an intelligent species might be able to recognize as what is called a semi-prime number, in the sense that it is actually the product of two prime numbers, in this case 73 and 23. And if they took that and then broke that down into a rectangle with 23 columns and 73 rows, and marked the various points in that grid where there's a 1, you would actually be able to produce this message that is in that burst of radio signal. Now, these were chosen very carefully, and I'll just go through this again very quickly. But what's shown in the top row here is an encoded way of counting from 1 to 10. And then this here shows something using this as a basis for numbers. This shows the various atomic numbers for elements that are very important to DNA, things like oxygen and carbon. These numbers here are actually, using those atomic numbers, are ways of indicating the formula for various organic compounds, which make up the various nucleotides in DNA. And this pattern here actually is an indication of the helical structure of DNA. And down here, you can actually see a person, basically to give an idea of who sent this message, a bipedal organism like us. And this here is a sense of the scale, the size of the being that sent this image. And this here is a count of the population of the Earth at the time that the message was sent, probably somewhere around 4 or 5 billion at that time. Now these dots here show again our solar system. Here's the sun and the 9 planets, well, 9 planets then, with the third planet pointing up towards, again, the origin of the message, a person. And then at the bottom, what is shown is a schematic of the Arecibo dish that sent the message and the scale of it at the very end. So actually, a lot of information has been communicated in just 1,679 bits. Who knows if anyone will actually receive this message? But again, you have to give them credit for trying something. So sending a message, though, is very difficult because we don't know where to look. There are so many stars in the sky. We don't know. We can't be doing it all the time. And really, the Messier 13 message from Arecibo was really something that was done mostly because we could, to prove that we could actually do this. And there has been, as far as I know, no dedicated effort to transmit a message out into the galaxy beyond that. There may be others, but I just have never heard of it out there. And it really is hard to know where would you send that signal. But it's still possible that that could be done. It's just something that isn't done very, very much. Instead, what we could also do, though, is broadcast a passive message. The Earth is producing lots and lots of radio emission on its own, just as a result of our producing radio broadcasts, radio, television, radar, things like that. And this incredible output of emission, basically related to our own civilization, is flowing out into the galaxy like a growing sphere that's basically as wide as twice the time that we have had radio signals in our civilization in total, which is something on the order of about 200 light years or so, given the idea that we've only had radio for about 100 years or so. And just to put that into perspective, what's shown on the right here is the extent of human radio broadcasts in the galaxy. And you can, if you get really, really close to your screen, you might be able to see that little blue dot there. Now that little blue dot, as you can maybe see in the slightly larger zoom in on the lower right, is actually to scale the size of that bubble that basically broadcasts our existence out into the galaxy. It's extremely, extremely small on the scale of the galaxy, let alone the fact that anything within that sphere is itself going to be very challenged to detect these very weak signals by the time they get out to that distance. I'm not saying it's impossible, but it would probably take a receiving area that would be gigantic to be able to detect that kind of signal. So instead, what we could do is perhaps receive a message. We could, maybe some benevolent alien civilization is actually doing the work for us, and instead of sending a message, they're sending us a message instead. And this is actually the basis of this movie, which I realized this afternoon is actually startlingly 25 years old almost, called Contact, which is the movie version of a book by Carl Sagan, who was a famous astronomer back in the 70s and 80s. And it's actually a really great book. And the movie's pretty good too, because it takes the subject very seriously and describes how a message from an alien civilization could be received and then interpreted, and what that could mean for society. A very, very good movie. I really recommend checking it out. But again, it's a work of fiction. We haven't actually detected anything yet. Well, anything with any certainty, but it's the basis of receiving this kind of message that has fueled a lot of the research into searching for extraterrestrial intelligence. Basically, SETI, the search for extraterrestrial intelligence, is based on this idea. And SETI has had a kind of a bumpy history over the last 50 years. It certainly is an imaginative program, and it basically has had incidences where it has stopped receiving public funds from very skeptical people. But nevertheless, it has been able to carry on mostly through private donation, because a lot of people think that it's not that expensive and it's still worth doing. And what the SETI folks have done over the decades is built up an enormous amount of data just by piggybacking on astronomical observations. So by piggybacking, I mean, for example, astronomers who would use Arecibo to measure various aspects of the universe at radio wavelengths could have some of that signal shunted to a nearby receiver, or that's able to take those signals and record them for later analysis. And this particular program is called Serendip, the search for extraterrestrial radio emissions from nearby developed intelligent populations. And it has gone through many, many generations over the decades. This chart shows, for example, the 5 of the generations, and it just shows exactly how challenging this process is, because even though Serendip, when it began back in the late 70s, when it began piggybacking on observations at the Hat Creek and Goldstone observatories, the number of channels that they were looking at, the number of discrete frequencies that they were trying to observe at a given time was relatively low. And it's really difficult to know whether or not you're tuned to the right frequency, even when you have just a handful of channels, because that signal could be buried in a wide channel. And you really need to narrow the channels down to be able to see if you've gotten the right frequency for which a possible signal could arise. So over time, because of advances in engineering and so forth, we've been able to get increasingly wider bandwidths and increasingly larger numbers of channels and refine that SETI work even more. But and that means that the amount of data that is produced is itself accordingly much larger. For example, even though we were looking at 100 channels back in the late 70s, now 30 years later, we're looking at 2 billion channels that are being collected with every observation from the telescope. Now, this could mean a lot for being able to look for SETI, but it's an incredibly huge amount of data to be able to analyze. Now, fortunately, the SETI people are extremely clever, and many of you may have heard about this, the SETI at Home program, which was an incredible thing where the SETI people came up with a screensaver that that could run on different computers that were not being used. So, for example, if you were doing work on your computer and you walked away for a minute, after a short time, the screensaver would run and use the computer in a way that wasn't being used by anyone else at that given time. And by having thousands of people doing this, you basically build up a huge distributed network of computing around the world that throws an enormous amount of computing power at a problem. So the screensaver, how it works is pretty clever. What it does is that when it starts off, it has to be connected to the internet. It connects to the SETI folks' database. It retrieves a small bit of data, and then it analyzes that data and looks for clues to see if there's something in the data that might suggest an intelligent civilization. When it's done that processing, it then sends that back to the servers at the SETI people, and then retrieves another patch of data, which it then goes through again. It actually is an extremely clever thing, and was I think maybe the first time that this sort of widespread distributed computing had been done when the internet became a more viable thing of communicating between people. There are other programs now that do this, for example, but SETI at Home was incredibly popular, and I think there were something like maybe 200,000 users that were downloading data at its peak. And unfortunately, over time, interest in it has waned, and it actually has stopped for a while because the team has built up so much data, and it's a relatively small team. It's only a team of about 3 people. They have a huge amount of data themselves that now they have to go through to see if there really is anything in all of that signal. I mean, it's so popular and is analyzed so much data that it really is overwhelming the people that have produced this SETI at Home program, and now they're actually needing to devote time to see what's out there. They're getting on in their careers, and they'd like to see something before they retire, and so they've made the decision to cease or pause the SETI at Home program so they can actually devote their energy less on keeping the program going and more on what the data actually says. So is that it for SETI research? Well, no. I mean, even though, as you may have heard, the Arecibo telescope collapsed late last year, and so it can't be used for piggybacking observations anymore. There have been new initiatives for SETI. And one of the most important ones, I think, is this new one called Breakthrough Listen, which is another initiative funded by this fellow here named Yuri Milner, who is using his own fortune to stimulate research into things that he finds particularly interesting. And the amount of money that's being offered here is quite considerable. He's using $100 million of his own money to fund SETI research for 10 years between 2015 and 2025. And what he's doing is basically allowing scientists to use time on the Green Bank telescope and the Parkes telescope in Australia, as well as a telescope in California known as the Automated Planet Finder, which is an optical telescope where they're looking for perhaps pulses, perhaps from extraterrestrial lasers, which itself is another possible way of communicating a message. So Breakthrough Listen has been going on, I guess, now for about 6 years or so. And has it found anything? Well, not really, but there's some intriguing possibilities there. And late last December, there was this very interesting message that, or news story that came out where one of the signals that had been recorded towards, again, Proxima Centauri of all places, actually seemed to have some kind of tantalizing signal out there. This object, or this detection, is called BLC1, or Breakthrough Listen Candidate 1, and it has been, I think, the most compelling possibility for there to be an extraterrestrial signal. It's a little surprising for it to come from Proxima Centauri, because Proxima Centauri, though it is the closest one, almost seems a little too close, because we wouldn't expect there to have perhaps a communicating intelligent civilization just next door. I mean, that would be awesome, but it does seem a little bit surprising. But also, Proxima Centauri is not the most favorable star to have a planet around. It's a star that's less massive than the sun. It's a red dwarf, as it's sometimes called, and its surface is incredibly active. Now, you've probably heard of solar flares, things where the sun burps and a bunch of gas goes flying out from the surface of the sun. Stars like Proxima Centauri have incredible amounts of burping going on all the time, and it has lots of flares which bathe its inner planets constantly with this radiation. So it seems like a very inhospitable place for there to be an alien civilization indeed. I will say that since this story has been posted, there hasn't been a lot of other information coming from the Breakthrough Listen people. All I know going forward at this time is that they have re-observed Proxima Centauri, and they have not found a signal like they found before. Now, what did they see? Well, in the first place, well, that itself is an interesting question. But they have not been able to replicate that detection, which is very disappointing. So it's looking like this is not going to work out, but they're probably still going to monitor Proxima Centauri just to see what was going on. Okay, so without Arecibo, and maybe without, if perhaps Breakthrough Listen itself peters out in a few years, we'll see if it continues to get funding or not. There are still other possibilities for searching for extraterrestrial signals. Now, this facility is something that basically replicates Arecibo's capabilities. This is the 500-meter aperture spherical telescope called FAST, which has been built in the last few years in the People's Republic of China. Now, Arecibo is itself just 305 meters in diameter, an enormous size, but FAST is actually wider by almost 1.5 times. So its surface area is probably more than double that of Arecibo. So that makes it a far more sensitive instrument potentially than Arecibo. And so perhaps it will be able to look for signals much more deeply into the universe than Arecibo could. In addition, one project that I am involved in is this next generation very large array, which is a project that isn't funded, but it's up for consideration for funding in the US. And I would sure like to see Canada join this, because I think it's a spectacular project. Now, some of you have maybe heard of the Very Large Array, which is an array of radio dishes in central New Mexico, each of which is about 25 meters in diameter. And there are 27 in a Y-like configuration, Well, the next generation Very Large Array is actually about 10 times that many antennas, about 265 antennas, of which most will be concentrated in central New Mexico, but some will be scattered at very large distances indeed. So in real time, they'll be able to synthesize images in the radio sky that are even better than what the Hubble Space Telescope is able to produce. These circles that are popping up here are showing the locations of other antennas scattered around southern New Mexico, and they will be put even as far as West Texas and southern Arizona, maybe even northern Mexico. And then a network will stretch all the way from Hawaii to the Canary Islands, going from west to east, and maybe as far north as Washington State. And we may even host ourselves a couple of radio dishes from the next generation Very Large Array in our radio observatory in Penticton, BC. Well, we will see, but it's a very exciting project. But part of what it could be used for is this SETI research, because all of that surface area, again, provides a lot of sensitivity for looking for signals. And I know that the SETI people are very interested in using it, perhaps in this similar piggyback manner, to look for these signatures from a technologically advanced civilization. There is another very impressive facility called the Square Kilometer Array that's actually being constructed soon in the southern hemisphere. And so with both facilities, we would have full sky coverage, enabling all nearby stars to be examined for such signals. Okay, so we haven't detected anything yet. Should we be worried? Well, I don't think so, because even though we've been at it for, let's just say about 50 years or so, that amount of time is still relatively small compared to, again, how much time it takes to be able to transmit signals across the galaxy. For example, that nearby civilization may not be very close to us at all. Now, this picture here shows basically a graphic of the disk of the Milky Way galaxy as a sort of cylinder, like a pizza, as I said before. And what's shown in the inner part is a cylinder that represents the propagation of that signal from our Earth that basically goes out into the galaxy. The question is, how big does that cylinder have to be to reach the nearest civilization? Okay, so using basic math and that Drake equation, you can actually determine, on average, how far is it that the nearest civilization could be. And using my relatively optimistic estimate of how many civilizations there are in the galaxy at this time, 20,000 or so, the nearest technological civilization is still maybe about 400 light years away. So we've only been at it about 50 years or so, maybe transmitting for 100 years. So maybe we're not quite there yet. I would like to say that estimate, again, may itself be extremely conservative and could be higher by factors of 10 or 100 or so, in which case that R number could go much lower. But I'm just saying that even though we haven't seen anything yet, it's not indicative that there's nothing out there. We have to be patient and give it time, especially since, you have to take into the account that if a nearby civilization were to detect us and wanted to send a signal back to us, that time has to be twice the time it takes for the signal from us to reach them, because they have to send one back to us. So in this example, it might take about 1,000 years to hear back from any nearby civilization, but still, those numbers are extremely speculative and could themselves be overestimates. Okay, so to end the talk, I'd like to describe something that is a very interesting point about the possibility of there being intelligent civilizations in the galaxy. And that's something known as Fermi's paradox. So Fermi, or Enrico Fermi, was a smart guy. He was a very important physicist in the early 20th century. He was a member of the Manhattan Project that helped build the atomic bomb during World War II. But he also won the Nobel Prize in Physics before the war in 1938 for his work on bombarding nuclei with neutrons and inducing radioactivity. And actually, he was responsible for the discovery of the various heavy elements called transuranium elements, which don't appear naturally, but can be created in particle accelerators for very short amounts of time because they're very unstable, but basically making new elements in atom smashers and so forth. So anyway, this very smart guy was out to lunch one day with his colleagues, and they were talking about UFOs, if you can believe it. And allegedly, what he basically said was something to the order of, if intelligent life is plentiful elsewhere in the galaxy, well, where are they? You know, where are they? And why don't we see them more often? And he based this statement on these very key facts about the galaxy, namely, the age of the galaxy is about 10 billion years, and the size of the galaxy is about 100,000 light years. So even though the size of the galaxy is huge, the age of the galaxy is much, much older. And to put that into perspective, a light beam going from one side of the galaxy to another could basically go back and forth from one side of the galaxy to the other about 100,000 times in 10 billion years. Okay, and so if you could imagine a situation where an interstellar civilization spread out into the galaxy, it wouldn't necessarily be, for example, going from one side of the galaxy to the other. Instead, you could imagine the civilization would expand by going to nearby stars, which would then produce themselves colonies or missions to other nearby stars multiple times, and then this civilization would then spread across the galaxy almost like wildfire. And so in that event, the galaxy should probably be fully colonized by whoever happened to figure out how to get to other stars first, just simply because there's been so much time for this to happen. How come we don't see evidence of this? How come we don't see like the galactic Starbucks in our shopping malls, for example? What's going on here? Now, there are many possibilities that can explain the Fermi paradox, and itself is worthy of an entire talk on its own. But there are, I think, about 3 different classes of answers to this question, and I'm just going to go through a few of them now. The first possible solution to the Fermi paradox is that it's actually, well, these objects that these aliens are actually already here. Now, I'm sure many of you have heard about UFOs, or what they're being described now as being UAPs, or unidentified aerial phenomena. Now, I will say that even though there has been lots of discussion about UFOs over the last 100 years or so, we still have absolutely no credible evidence that there are any UFOs out there, that we are being visited by alien species at all. This is another whole talk on its own, and it's becoming probably even more prominent because there has been this recent release from the Pentagon, by the U.S. military establishment, that various Navy planes and so forth have been seeing things that they don't understand. Now, they're not saying it's aliens, but they're not saying that they also are the reason for these peculiar objects being seen. And there's lots to say that these things are not real, because, I mean, as a species, we could be fooled 6 times to Sunday. It's incredibly easy for us to be tricked. And there are many ways that the apparent behavior that these UFOs have shown, these UAPs have shown, could be explained. But so I think the jury is still way out on whether these are really proof that aliens are actually here. A corollary of this is that maybe we are the aliens, that perhaps the civilization that first arose in the galaxy seeded the galaxy not so much with themselves, but with the stuff of life. Basically, seeds were spread out through the galaxy, and where they found purchase on promising planets, life was able to develop. Now, again, we don't have any proof of this, but it might be an interesting way to solve the fact that perhaps it's a different way of colonizing the galaxy than actually sending people or beings out into the galaxy instead. Another possible solution to the Fermi's paradox is that they exist, but they haven't yet communicated. And one way of interpreting this is perhaps that, well, maybe the ways that we are trying to communicate are just simply not up to snuff. Maybe observing or communicating by radio is not a good look. Maybe it's the wrong way to approach interstellar communication. Maybe advanced civilizations have way better ways of communicating that we aren't able to tap into. Maybe it's like we're trying to connect to the galactic internet using carrier pigeons or something like that. We're just not interfacing in the right way. We'll see. I mean, I think radio is a very economical way of communicating, but it would be, I think, a surprise that. So I think it would be a surprise that radio wouldn't be used in some ways. But again, it's hard to know. Another possibility, which has also gained popularity thanks to the series of novels by science fiction author Cixin Liu of China, is that there's a tremendous reluctance between civilizations to communicate with each other, because in this universe that he created, species are extremely competitive, and any sign that a civilization has asserted itself in the galaxy is quickly met with overwhelming force to stamp out the possible competition for resources in the galaxy. And I think it's an extremely bleak and harsh way to imagine alien life. Good grief. But I think that such a universe would almost be unbelievable, because for the very good reason that I think that there's plenty of resources to go around in the galaxy. There's really no way or no need to be so competitive. I just don't buy the whole invasion or preemptive extinction argument at all. It just seems like a really bleak thing to even consider. So the third possibility, of course, is that, well, these alien civilizations simply don't exist. Okay, we're the only ones in the galaxy that could be considered intelligent. Now, why that is? Well, maybe we're the first civilization out there. We're the first kids to get out there, the new kids on the block, and so someone has to be first, though that does seem rather unlikely. But if we are the first, then the galaxy is our garden. We can go and do with it how we will. That's disappointing from this possibility of being able to maybe learn from much older civilizations. But who knows? Maybe we're the first out there. Perhaps a little bit more depressingly is that maybe they don't exist because maybe all civilizations reach a point where they simply cannot progress. Perhaps they run out of resources, or they're unable to maintain their technological society, and there's some process out there called the Great Filter, if you will, that says civilizations have to be short, because their lifetimes of civilizations have to be short, because they're just simply unable to sustain themselves long enough to exist for any other civilization to even detect them at all. Again, an incredibly bleak and unpleasant thing to look at, but nevertheless, it's not totally out of line, especially since we are ourselves facing very difficult and challenging times ahead with regards to climate change and resource depletion, for example. I'm not saying we're not able to get through this bottleneck, but I'm just saying these challenges do exist, and maybe there are challenges out there we just simply don't comprehend. I think that's a really depressing answer to the Fermi's paradox. I'm an optimist, and I think that I would like to see civilizations, simply because there's the possibility that they can last for very long times. And it is indeed that very argument that I think is also an extremely compelling reason why we should devote a small amount of time and a small amount of resources for the search for extraterrestrial intelligence. I mean, if you look at the Drake equation, this this number n, the number of communicative civilizations, is linearly dependent on that value of L, the lifetime of that civilization. So, I mean, if we detect a civilization, well, basically that means that the greater the number of civilizations, on average, the closer those civilizations are going to be in the galaxy, and the likelihood that we will detect them sooner than later. So if we detect a civilization soon, I think it implies that the lifetimes of civilizations can be large, and thus perhaps our own civilization may be able to last itself a long time. It would be proof that civilizations can pass through the bottlenecks that could restrain them, or constrain them, and then be able to flower in ways that we aren't able to yet comprehend or understand. So in closing, I'd just like to say thank you for listening to my talk tonight. I'd just like to summarize by saying, again, there are no definitive detections of extraterrestrial signals yet. There are many searches that are ongoing around the world, and these will continue for the foreseeable future. Given the scale of the galaxy and the finite speed of light, it may take a while, a wee while, as my mom might say, but we must be patient, because I think if people are willing to devote their lives to this, we should just let them and see what happens, because the payoff could be incredible. So, but again, I think it's important to note that we ourselves need to be around long enough to be able to communicate with our neighbors. And so let's do what we can to make our own civilization last as long as possible. Thank you very much.
Wow. Thanks, James. I've taken reams of notes here. I've got notes all over the place for this, so that I can remember some of this for sure.
I guess I went over. Sorry.
Oh, it's okay. Hey, we're all good. We're all good. Does anybody have any questions that they'd like to ask James? I've got a couple, but anybody has anything that came into the chat or
I haven't
on the
received
Q&A?
anything in the chat yet, but I did have a question of my own.
Okay.
I was curious if you knew more about that Arecibo message and how they sent it. Like, what did they? How, like you said, they were basically rectangles of zeros and ones.
Yes.
But was it just a single burst? Like, what was a zero represented by, and what was a one represented by, and did they repeat the message at all?
I don't think they repeated the message, but given how much press this message has created, you'd think they would have done more than just sent it once somewhere. I mean, come on. But nevertheless, I think what they did is they modulated the signal. I can't remember the precise frequency they used, but what they did is they shifted that frequency at certain times to produce basically times when it was at one frequency and times when it was at another frequency. And that was what created either the one or the zero. And so by doing that, they were able to send out this series of frequency modulations that allow them to produce that message.
Cool, thanks.
Okay, Scott says, in my Search for the Life in the Universe course at UVic, I was asked to decode this message in a lab. I did not come close. Well, I myself, I think, would be quite challenged by that. I mean, I think the hope is that a lot of aliens would look at this and try to figure it out, and maybe someone would figure it out. But it is not obvious at first glance what you're looking at when you see that message.
No. Yeah, you can see the one from Reg there, James.
Yes, he asks,
Yeah.
do you think that the data collected by the CHIME survey could be of value to Breakthrough Listen? I think that CHIME doesn't have the ability to, it doesn't have the number of channels that might be needed to look for this kind of signal. I guess it's possible in the sense that maybe it, in its sort of rather passive mode, it could actually pick something up. The way CHIME, for those of you who don't know, is this new facility that has been built out in Penticton at the Dominion Radio Astronomical Observatory. It's a very novel design. It's a radio telescope that basically points straight up, and as the Earth turns, it basically scans the sky. And CHIME has been excellent for examining things in the universe that apparently go off either randomly or even by with a lot of regularity. For example, it's been doing gangbusters detecting this mysterious new phenomenon called fast radio bursts, which are these millisecond long flashes of radio light that no one really understands where they come from. There are many theories, but they may be, for example, magnetic fields breaking down around neutron stars. But CHIME is detecting more than any other radio facility out there. So with this capability, maybe it would chance upon the transmission of a signal. Now, CHIME's frequency range is much lower, I think, than what's considered to be the de rigueur frequencies to look for intelligent signals. Those are usually between the hydrogen line, or the hydrogen frequency I was telling you before, 1.4 gigahertz, and the OH, the frequency from hydroxyl, which I think is about 2.3 gigahertz. I may be wrong. So looking at that so-called water hole is where a lot of emphasis has been placed. And so it's not looking at those frequencies, so I don't think it would do a good job of seeing them. But good idea though, Reg, well done.
I was just thinking, James, that you might get Yuri Melner to send some money towards the CHIME project.
That would be awesome.
Just not.
So Yuri Milner is an interesting guy. He actually has a home in Saanich. But I haven't knocked on his door yet. I don't know how often he comes to Vancouver Island, but he does have apparently a home here. So that's interesting. So Dave Payne asks, does quantum entanglement offer the possibility of communication faster than the speed of light? That is an excellent question, Dave. Thank you for bringing that up, because in an earlier version of this talk, I actually thought about including this as an interesting workaround to the limits of interstellar communication that I had described. So what is quantum entanglement? Well, this is actually itself worthy of an entire talk. And it's an interesting way of perhaps being able to communicate basically instantaneously, regardless of distance. And the way it fundamentally works is that due to a quirk in quantum mechanics, which, believe me, is full of quirks. So basically, the way quantum mechanics works is it's really a matter of understanding probabilities. And the way the physical world is on the extreme microscopic or atomic scale is that things exist in a very uncertain form. That where, for example, where an electron is not extremely well understood. It could be over here, it could be over there, it could be up there. It's just in this cloud, right, of probability. And being able to isolate where it is not easy. And there are various uncertainty principles. There is an uncertainty principle that helps define how hard it is. So you can find out where an electron is, but you don't know how fast it's moving then. So there's a bit of a trade-off. Okay, so quantum mechanics is weird, and one of the weird things about it is that with this cloud of uncertainties that everything on that scale exists on, if you're able to, for example, find something, if two things go off in different directions, for example, and they're in this quantum mechanical state of unknown, then for example, if in one of those things actually becomes understood, it gets observed and becomes better understood than a cloud. Like, for example, it's the spin of the electron, for example, is pointed in one direction. Due to conservation of momentum, for example, if another electron had been created and gone in the opposite direction and its own sense of uncertainty existed, then the identification of that particle with a given property at one location would actually define the characteristics of that particle in the opposite direction, even though there's no way that light could have communicated between those two particles. So it's an interesting workaround, which says that if the state of something at some great distance over here can be known, then we can actually understand something instantaneously at a much greater distance. Now, you may think that's bunk, but actually it's being shown to be used, and there are experiments that have been able to demonstrate this from very large distances, even in orbit, like that has shown that you could actually in one hand determine something that then instantaneously is able to produce something far away. It's amazing. So what does all this prologue mean? If you were able to take those things that were entangled in a way that I've just described, and you were able to take one of them and move them to a vast interstellar distance, for example, if you were able to change the state or define the state of the one near you, you would then define the state of the one at that interstellar distance. So that would be a sense of communication, because you could imagine, use your imagination a lot here, to have some system where basically by defining the states of things locally, you then define the states at something at a distance, and then you're basically communicating. If those defined states are able to themselves be some kind of message or could be worked out in some way. It's incredible to think of. And when I said that radio is passé, I actually thought that maybe this was actually some cooler way that aliens could communicate, at least with themselves, that they could then send out, I don't know, fleets of robots or something like that that go out into the galaxy, seeding the galaxy with these communication devices that then are able to communicate back to the mothership instantaneously because of their of this incredible quantum entanglement effect. It's kind of mind-blowing, but it is a very interesting idea. Thanks for bringing that up, Dave. I as you can see, I wanted to talk about it, but I think I talked way too long as it is anyway. So.
Okay, I think. Oh, is there another burning question that people have anywhere? No. Okay.
No, it
Well,
seems
thanks,
that
James.
Chat on YouTube and is pretty quiet. Nobody's got any questions.
Yeah. Okay.
So yeah, that's it.
Well, thank you again.
Yeah. So James, I'm thinking you've said about 3 times here that's another whole talk. So yeah. We've got about a year and a half worth of talks that you've set yourself up for. So that's great.
I'm always
okay. Thank you so much, James. That was great. That was awesome.
Thank you so much. Thank you.
Oh, terrific. Okay. I think because we are a little kind of compressed for time here, I had a little note from Calvin saying, or from Aaron saying that maybe he could put off his eclipse pictures until the next time, and we could show those because those are going to come. And I'm wondering whether or not we could kind of go into the Ask an Astronomer question and answer thing right now. Patricia and I were doing some work on the summer solstice, but that actually could also be kind of put to the next time because we'll be just past the summer solstice the next time. So Patricia, is that okay with you? I know you're just on the telephone, but maybe we could put that away. So I think what we're going to do is go right into our Ask an Astronomer section right now. And I'd like to get Reg Dunkley and Scott Wilkinson on highlighting, if I could, and you could take me off, Calvin, completely. Thank you. And we could get going. And I'm wondering if any questions had been sent already to these wonderful people. to get the ball rolling?
Like I said, the folks over on watching us on YouTube are pretty quiet and cozy
Okay.
watching us. There are currently no questions on the chat, but we could also can kind of continue and spin off the discussion that we had about radio communication and trying to communicate with aliens. And if anybody comes up with any questions, they're welcome to put them in the chat and we'll get to them.
Yeah.
I've got a couple of questions here, Calvin, that we could get started with.
Excellent. Okay.
Go ahead, Amy.
So first question is, how do we measure a galaxy's distance?
Reg, do you want me to take this one?
Sure, go ahead, Scott. But before you do, I just wanted to say congratulations on getting your bachelor's degree, and all the best as you go forward on your master's. It's a pretty exciting project. That's wonderful. All the best.
Thanks, Reg. It's a pleasure to be up here with you, and looking forward to answering some questions. So thank you for that. Distance to galaxies. Someone must have paid them to ask this question. We were talking about this earlier this week. There's actually one of the fundamental things that you learn, as Reg was saying. I just finished my Bachelor of Science in Physics and Astronomy. One of the biggest things that they try to ingrain in first year astronomy and throughout your bachelor degree is how to measure distances, because it's not simple. You can't travel to these places. If I want to measure the length of my desk, I have a unit and I actually go and I do it. You can't do that with something like a star or a planet even, or nonetheless galaxies, right? So we actually have something that we call the cosmic distance ladder. And it's called the ladder because you have to build each rung from scratch. Okay, so you can start maybe with, I'd say the lowest rung is probably radar. You can bounce radio waves off of Mars and you can get a rough distance. We know, as James was saying, that the speed of light has a finite speed. And so you send the light there and you wait for it to bounce back. And the time that it takes is a distance. That's a unit of distance. So now you've calibrated the distance to Mars. You can use something called parallax. Parallax was a huge fundamental one, and it goes all the way back to, I think, ancient Greece is where they started using parallax as a proxy for distance. Now, parallax is simply, we could all do it at home. The classic is if you stick your thumb out at arm's length and you blink your eyes back and forth, you'll be able to, relative to the background of your wall or whatever you're looking at in the background, your thumb will appear to move. And the amount that it moves, it'll move. If it's closer, it'll look like it moves more. And if it's farther away, it'll move less. And that's parallax. And for that, we can get out further. We can start measuring stars. The newest Gaia mission is using parallax to high precision. You can measure all the nearest locations of all the stars and so on and so forth. And so then you could then calibrate this using Mars as a distance, and that's how you calibrate the next rung in your ladder, right? Because you have to calibrate that parallax and so on and so forth. Then you keep moving, you go on all the way up the ladder, and now there's several different ones. We were talking about Cepheid variable stars that have an intrinsic light curve you can identify, and they're going to have a unique absolute magnitude. And based off their apparent magnitude, you can use distance dimming of the light to figure out how far away they are, calibrate it using parallax. And you continue to go up the ladder until we get to the most distant galaxies in the universe. And we use something called the Hubble La Metro Law. So it was originally just the Hubble Law, but then whatever political reason there was, it's now the Hubble La Metro Law. And that's simply that due to the expansion of the universe galaxies that are farther away will appear to be moving faster away from us. So the speed at which they're moving becomes a proxy for the distance to that galaxy. And the speed at which they're moving away can be measured using their redshift. And so you can measure how redshifted they are, the Doppler shift of the wavelength they're emitting, and that will be how fast away they're moving. And because the universe is expanding, not just as it is, but the units of space between us and that distant galaxy are actually, the actual units of space are all expanding together. And that's these aren't just moving farther away from us. They're actually just farther, and that larger distance causes a bigger apparent speed. And so that's actually, this kind of redshift measurement is a proxy for distance. And so when I research galaxies, eventually you give up listing distances and you just give their redshift, because that's more of the intrinsic value. And so I don't typically plot things as a distance, I plot them as redshift. And I hope that answers whoever's questions there.
Awesome. Thank you. Okay, next question is, can a star turn into a planet?
Reg, you want to take that one?
Well, we'll see. I first of all, that was a very nice description I heard there, Scott. So well done on that. For a star to turn into a planet, I guess first of all, it has to become dim enough so it's not emitting a lot of radiation. Like Jupiter actually emits more radiation than it receives, so it's kind of a very a failed star, or something like that. So if you to be a planet, it has to orbit something else. So let's envision a binary system, and maybe it was a star at one time, and it was a pretty feeble star, and maybe it ran out of enough fuel that it's not radiating very much light or even infrared information, and in that way it could be downgraded to a planet. That's one argument I would put forward. Maybe you have some thoughts on it, Scott.
Yeah, Reg, I'm glad you started that one, because I would have been a little bit more blunt. My original thought when I heard the question was no, it cannot. But I like what you did there is the line between gas giant planet, because when I think planet, I think Earth, I think Mars. That's not actually fully true. That's only half the planets in our solar system. But the actual the line between Jupiter, a gas giant, and a star, or a dwarf star, or just those types of stars, is actually a very, very fine line. And so if it was just barely a star, barely had enough mass to undergo fusion in its core, there's a chance that it might deplete itself quite quickly and become something like a large Jupiter. So that was a very creative answer, Reg. But by and large, this is not a common thing that happens in the universe. So I'll put that up there.
All right, thank you. Question Reg might be the best one for this one. How different is our atmosphere than the atmosphere on Venus?
Well, it's spectacular differences. There's an awful lot more mass to the atmosphere of Venus than there is to the mass of the Earth. I don't have the figure, but I think it's somewhere in the neighborhood of maybe 80 times, or maybe it's 800 times more the pressure at the surface of Venus is probably close to at least 100 times greater than it is on Earth. And it is also very hot because partly the compression under that weight. The mean temperature on Venus is around 800 degrees, which is the melting point of lead. And the composition of the atmosphere is quite different. And this is really a relevant question this week because 3 different missions have just been announced that they are going to be sending space probes to Venus. NASA has got 2, one called Da Vinci and another one called Veritas. One is going to, the Da Vinci system is going to be sending a probe that will be doing some sampling of the atmosphere and the composition of the atmosphere. And the plan is to actually drop a couple of 1 or 2 probes down there, I think. The Veritas project is to use basically monitor and use radar to probe the structure of the planet, the physical structure of the surface of the planet. Meanwhile, the European Space Agency has got a thing called Envision that they're planning to launch. And I just spent the other day reading about it. And they gave a detailed plan of it. And I was kind of shaken because they're planning that they're going to start their first results might get to us by around 2035. And I started to wonder if I'm going to be around when the results come in from that. So it's wonderful to have these 3 different projects together studying this because Venus has been kind of the Rodney Dangerfield of planets that it hasn't been giving the respect that it deserves because basically it's a runaway greenhouse effect going on there. And by studying that, we might be able to learn methods to prevent Earth from going in that same direction. So this is really very good news, and I'll leave it at that.
Thank you. Now I have a question for each of you. Can you tell us what your favorite constellation is and why?
I would have to think. Reg, do you have yours on hand?
Well, I'm not a very imaginative sort, and I guess with constellations, the legends with constellations are such that it was kind of the first Netflix. That was what people did at night, is that they talked about stories involving the stars. But I don't have the imagination to actually visualize the pictures that these people are seeing. So the only one that I can really agree on is Orion. It's a beautiful thing. It's got a belt, and it's got a kind of a fuzzy sword there, and it's got and a place where you might have a bow and arrow, and it's got a big arm up, and it's kind of plausible, and it's beautiful. And when I first see it, when it starts rising late fall or early winter, it's like an old friend has come back to visit. So that would be my favorite.
Right, that was a great pick. I should have swooped in first and taken it. I also connected a lot with Orion as a kid and growing up. Just always, because even if you can't identify all of Orion, the belt it's a great place to start, and then it all folds in. There's so many things going on in Orion. There's stars that might be exploding soon. There's there's a lot of amazing things. Nebula to look at, galaxies within, and it takes up a whole portion of the sky. It's really nice. I guess the second to that is I really enjoy in the summer being able to point out relatively easy to spot ones, simple ones like the W of Cassiopeia, the Southern Cross, things of this sort. And with those ones, well, or even Cepheus, or in Cree legends, Mackinac the turtle. These ones are they're my favorite just because I can spot them. Things like Draco or Perseus, they start to really become, as Riz was saying, you really got to be using your imagination. The patterns aren't so simple, and it's hard to connect with and explore the sky with your friends and family. So simple ones like Cassiopeia, Cepheus, Southern Cross, I guess that's Cygnus as well. Those ones I connect with a lot. But I ended up falling in love a lot more with, I'm technically an observational astronomer, but I really love the stories that the physics tells, not necessarily, I started by looking up in the night sky and really found my way thinking about the stories that follow. And so, I don't know, that's where I find myself.
Maybe, Scott, you were looking at the northern cross, the Southern Cross we can't see from here.
Thank you, Lori.
You're welcome. You should have put it on Jeopardy.
It's a big cross in the night sky. Sounded fancier. There you go. Thanks, Lori.
Wonderful. Okay. Do either of you know how many stars are visible in the night sky from Earth?
You're unaided by not using a telescope.
Unaided.
Yeah, I
Yeah,
think
unaided.
6,000.
Unaided. Because my answer was going to be it depends. Because I remember I ran into this problem. So a big part of my research was I'm looking at galaxies from the Canada-France Imaging Survey. So it's a large survey, and Stephen Gwynn here at the NRC, some of you might know, I was talking with him, and he said, could you do what you've done, the calculations you've done for a small set, for the entire sample of all images of all these galaxies? And I said, how many galaxies is that? This is just a small portion of the night sky. And he goes, well, it depends. What magnitude limit are you willing to go down to? So the eye itself, we're not very good sensors. The retina is not great. We've evolved past that with all of our amazing technology. And so the amount of stars depends on what wavelength that you're tuned into, and how much time you spend looking and collecting data, because you can see a lot. You can see very, very far if you spend a lot of time and a lot of money. 6,000 is a better answer.
Yeah, that's we go out and count one night. Yes, Lori was just mentioning that, yeah, owls can see more than we can. So yeah.
And to that point, it's going to be different for every person, because every retina is not going to be identical. So how faint you can see is, and how many you'll see is going to vary from person to person. Although, not by.
Speaking of that, and this is Scott's fresh from the academy and everything like that. Being a person of advanced years, I've got to send out a warning to you. A person's vision does not improve with age. So don't let those photons go to waste.
So I'd better get counting now. There we go.
Oh. Okay, and then just a last question for each of you again. A little bit about why astronomy is important to you. How did you come to this? I think Scott kind of started talking about that a bit, but how did you fall into this in your life?
I can go first.
Okay, Scott.
I was going to suggest, as mine happened more recently, I imagine. Okay. But I remember it really wasn't that long ago, right? So I started university 4 years ago, and so around 5 years ago, I knew I wanted to go into the sciences, but I didn't necessarily know what I wanted to do. What do I want to spend the next 10, 20, 30, 40 years of my life thinking about studying, what am I going to invest my time into? What types of questions do I want answered? And it was fairly simple. And a lot of high school students ask me, how did I find my path? And, and it's not super helpful, but I really just thought about what type of question do I want to answer? What are the questions that keep me up at night that I'm going to be juiced and amped to attack every morning? And that was the big questions about, by studying even a small portion of astronomy, you are contributing to questions like, where did we come from? Where are we going? Mm-hmm. And the experience that I've found in a simple 4-year degree is you explore out into the cosmos, and then you look back with a new perspective, and you see we're not so different from one another. Our temporal length, the time that we spend alive and conscious on Earth, is minuscule, and that we should be happy and joyous and peaceful as much as possible. And so that's kind of where I came from and where I've come. But that's how I got into it. Reg, what's your story?
Well, it's in my case, it's an epiphany, and it occurred when I was in grade 2. The Soviet Union had just launched Sputnik, and the United States were highly embarrassed, and they thought that their children were imbeciles, and they said, enough of this baseball cards, bring out space cards. So in grade 2, instead of buying your bubble gum with baseball players in the cards, they had a series of about 100 space things. And so I saw one of these things, and the card that did it for me was saying, they had 2 spacemen out there discovering a new sun. And I thought, what? There's more than one sun? You mean those stars are suns? And that was such a revolutionary thing to me. I was just blown away. And that was my on-ramp to astronomy. And it was a wonderful thing to happen. And that's basically it. So it happened way back when.
That's wonderful. Thank you both for joining us tonight and answering these questions.
Okay, thanks, Reg and Scott. Thank you, Amy, for hosting the Q&A. Next time we'll get some other people to come in. We're going to see if we can get different groups of people to come in to be our guest Ask an Astronomer. So some of you people that are online, you might be asked. Yes. So we're going to move through to David. To David Lee right now. And David is going to start off with just a shortened version of what's up in the sky. If we ever actually had a sky to look at, he'd start with that. And then he will work into some of the EAA that is there. And we've got Dave and Brock with him. And Scott, you're still going to be on, so he can work away. So I'm going to hand it back over to David. Thank you, David.
Well, good evening, everybody. I just I'm amazed by the insights and the conversation so far, but there's more to come, so don't go away. So I'm just going to share my screen with you. So I think I'm not going to spend a lot of time on this tonight. This will be kind of foreshadowing things to come. I'm just going to talk about a few concepts with you, and then we're going to move into EAA. So between now and the next time we meet again, I wanted to tell you a little bit about where all the planets are right now. Some are in the evening and some are in the morning. And then talk a little bit about the moon and what we're going to be able to see. And then there's a conjunction coming up. And this is where I want you guys to really kind of plan ahead a little bit. go look for a couple of planets and then watch how the distances between them evolve over time. And then just a very common asterism that's in the night sky, and something we're going to see all summer, and then something about a double star. So the evening planets, Venus and Mars, I think if you wanted to see Mercury, we've kind of missed that now. It actually sets before the sun actually sets, but we can still see Venus setting. So I remember seeing it last week sometime, and it's very, very pretty. It does compete with the fact that the days are quite long now, but it does pop. Like, it does pop out. It's a very, very bright planet. And if you wait a little bit, and then you might engage with some binoculars, you should be able to see Mars as well. Now, if you're an early riser or you're a late to bed person, you should be able to see Jupiter and Saturn in the early morning right now. And but just remember, the Saturn's a little bit dim, so you might want to use binos for that. Jupiter is very bright, though. Have a look at that little link down here. We'll talk a little bit about it maybe the next time. It's quite interesting comparing the magnitudes of the planets. It's actually surprising in some cases how some are brighter than others that you wouldn't expect. And it all has to do with their position with respect to the sun. But more on that in the coming star parties. The moon, wonderful subject every month. And between now and next time, we're going to see a first quarter moon. And during this phase, it's really wonderful watching and looking along the terminator. The other thing I would like you to do between now and next time is see if you can identify the seas or the maria that are visible at first quarter. You can see if you can identify which ones those are. And another thing to note is with first quarter and third quarter, this is the time when we actually see the moon during the day. So in the first quarter, we would see it from maybe past noon, from 1 o'clock till about midnight. And then in third quarter, you see it all night if you stay up all night, and you'll see it up to about noon the same day. So if you ever wondered when to see the moon during the day, that's when you do it. Okay, so here's one that's coming up, and this is going to take time. What you're seeing right now is Mars and Venus coming closer and closer together. So starting tonight, they're relatively spread apart, but by the time we hit around the 11th or so, or the 12th, we're actually going to see them very, very close together. We're going to see them probably about half a degree apart, actually. So that's on July 12th. Summer asterism. So this time during the summer, you should be able to see 3 bright stars, and we call this the summer triangle. It's an asterism because it's not an official constellation, but we have many of these shapes that we see up in the night sky. Now, it happens to be quite large, just like the Dipper, but there's small asterisms as well. So there's one called the coat hanger, and again, we'll talk a little bit more about how to find it, but in the meantime, if you want to hunt yourself, take a pair of binoculars and draw a line between Vega and Altair, and then scan along that line. You might find something surprising. You might find something that you find in your closet. So double stars. We're going to spend a lot of time on double stars over the summer as well. There's one actually at the head of the constellation Cygnus, and this is a beautiful one. This is one that we always talk about on Saturday nights, and this is called Alberio, and this is the head of the swan. It's Beta Cygni. It's composed of an amber and a blue star. And the reason why we often use this as a demonstration double star is that you can really see the differences in the colors when you see them together. Again, everything I've mentioned so far is either naked eye or binocular friendly. So no need for the big guns. You can see a lot of this just with your eyes. So just a reminder about the solstice. And this is the talk that Lori and Pam didn't get to give, but summer solstice falls on June 20th this year at around 8:30 or so. Yeah, the longest day and the shortest night. And much to the chagrin of the next group, I'm going to introduce a couple of people I've been working with the EAA group. This is where we go beyond using binoculars and using just our eyes. We're going to use a little bit of help from electronics. So I'd like to introduce Brock Johnson. He's with us tonight, and also Dave Payne. Now, both of these guys have been extremely prolific, more prolific than I am, which is why they're here. But anyways, I'm hoping to bank on a lot of pre-recorded material. I can actually hear the rain outside right now, so I know it is not pretty for telescopes or electronic sensors. So I'm hoping to have the sort of a continuance of this kind of lively conversation that we've had tonight. I think we're going to see a selection of galaxies and maybe some nebula and maybe even some clusters. So I'd like to hand it over to Scott, and let's have a look at these images.
Yes, let's. Brock, Dave, is there anywhere you want to start, or am I taking the reins here?
I think you're in charge.
All right.
You're totally in charge.
Okay. Wow. Look at all this power. My gosh.
Careful.
I had an idea, and I think we should run with it. I'd really like to start with maybe Dave, your Flame and Horsehead Nebula, what you call it, or what I might even add would be more applicably the Orion Molecular Cloud Complex, as there's lots going on in this image, but featuring.
Do you have them, or do you want me to bring them up? Or
if you could bring them up, that'd be great. But I guess I could as well.
It would be easier for me right now for you to bring them up.
Okay.
You can go ahead and share your screen, Dave.
It's going to take me a second. Sorry, I was not prepared.
Yeah, no problem. I can see the wheels churning in Scott's head.
Yeah, do we want me to, Dave, I could go to your Zenfolio page and
yeah, that's where I'm just going.
Okay, sure. I got it. Ready to go. So this is where I'd like to begin with the evening. So this is our EAA session, so electronically assisted astronomy. Now, certainly in need of the electronic assistance tonight, as we can't actually be on Sky. But this is where I wanted to begin, as I think thematically, at least, there's a lot of beginnings in this image, right? This is what's called, there's a lot going on in this image. I think it's a beautiful image from Dave. And this is really the entire image is an image of the Orion Molecular Cloud Complex. And it's called that as it is a molecular cloud. There we've got gas, dust, a lot of ionization going on. But a few things I'd like to point out. So first, the big targets, the big fancy ones, let me change my coloring here, is common ones that we've seen. You may have seen a close-up of this one. You may have seen a similar view as this before, but this is what's known as the Horsehead Nebula. Now, it's called this as it resembles a horse head. I think it resembles quite closely the knight piece on a chessboard. I hope that's where it got its name from. That's what I see when I look at it. And when we look at this, the Horsehead Nebula it's darker than the rest, you'll notice. So the light we're seeing is what's called emission. These are emission nebula. And what happens is, as I was saying, this is the beginning, a lot of beginnings happening here. A nebula is the birthplace of stars, solar systems, planets themselves. We start with a diffuse cloud of gas and dust. And there may be a disturbance, there may not be, but through whatever happens is there's a collapse in the cloud, often many different collapsing clouds, and they collapsed into, they collapsed dense enough to form a star fusion. And as they collapse, there's the conservation of angular momentum, there's the rotation. And so you get the spin of the star itself, a protostar initially, and the planets that form around it. And when Carl Sagan and Feynman and all these great physicists and astronomers from our past, when they say that we're made of star stuff, this is where we come from. This is our beginning. I can envision billions of years ago, the sun itself may have originated in a location much like this. And anyways, I'm getting to my point here. When that star collapses and eventually becomes dense enough to ignite hydrogen fusion in its core, it then emits high energy radiation, ionizing radiation. That can be enough to completely remove the electron from hydrogen or another atom, or just to excite that atom. Either way, those electrons fall back down and give off specific wavelengths that we can then see with our telescopes. And then the horse head itself is it's a much denser, it's larger particles of molecular gas and dust that then block that emission nebula. And so that's what the Horsehead Nebula itself is really gas and dust blocking the emission. If you were to look in the infrared, that's specific to this wavelength. If you were to image in the infrared, which we have not, it would actually glow and the rest would fade as it emits a black body radiation relative or according to its temperature. Other features to note in this image include the Flame Nebula on the left-hand side, which I think is just absolutely fabulous. And in the coloring and the filters used here, you can absolutely see why it's called the Flame Nebula. It literally looks like a little piece of flame itself. And similar features are going on here. This is the birthplace of stars that are giving off light and exciting the gas around it. That gas is what we're seeing. And the dark spots are the molecular clouds blocking that light. And then a lesser known one in between, this is NGC. I don't think there's a name for it other than NGC 2023. And this is there's a star inside that's lighting up the gas around it. And it's actually reflecting off some of that dense material, the same material that is making up the Horsehead Nebula itself, and then reflecting back towards us. So it's an emission and reflection nebula. And of course, there's also filamentary structure that you can see. This is extremely important, and I think it gives way to the name, the Orion molecular gas or molecular cloud complex. This is a very complex and diverse physical creation, and the filamentary structure is often a result of magnetic fields from all these charged ionized particles moving around. You can see plumes of gas and dust, all with unique and diverse kinematic structures. And so I thought this was a great place to start our night, as many beginnings are happening in this image all at once. And in some sense, we're seeing our own beginning somewhere along the line. And I'll add, if at any point anyone has questions or comments or thoughts for me regarding the physics, or for Dave and Brock regarding how these images were captured, feel free to go away. Someone might have to relay them. I might not be able to keep track of the chat box.
I had one quick question.
Please.
You mentioned something called NGC 2023.
Yep.
I thought NGC stood for New Galactic Catalog.
Yes, common confusion, New General Catalog.
Oh, okay, thanks.
No problem. Okay.
So just one thing, just before you leave that, Scott, over to the left-hand side, there's a star with a red kind of puff around it. Yeah, just where you have your cursor.
Oh, you guys can see that. That's nice.
Yeah, is that like another where the star is just reflecting all that gas? Like, are the gases being reflected by the light of that star?
Now, while I can't say with 100% confidence, I would say with large confidence that yes, that is what it appears to be to me, to my eye.
Okay.
That seems to be what's happening there. Yes.
That's a fabulous image, Dave. That is just, it is wonderful.
Thank you.
May I please have one to put on my wall, please? I'd love it. It would be gorgeous. Yeah. Oh.
There truly is beauty in the complexity of this image, and also a few notable features that you may have seen before. I really like this image and didn't want to leave it out.
The only thing I'd add is you were talking earlier about Orion being your favorite constellation.
Yes.
And this is, I think it's the middle star of the belt.
Right.
So next time you're out and you're looking at your familiar Orion, there's more there than you can actually see with your eye.
Definitely. I agree. Yeah. And so that's where the name, the Orion Molecular Cloud Complex, come from. So
yeah.
Right within Orion. Like I was saying, a lot of things going on inside Orion that you may not, you can't see with the naked eye. Now, Dave sent me this image almost as a joke. As I find there's so many images, they're beautiful images of other nebula, but the physics, while they're all diverse and complicated, the overarching themes are much the same, and lots of beautiful imaging here. And but on my end, I actually find that it gets a bit repetitive. So as beautiful as a lot of these images are, one that I actually want to point out, though, a little caveat that I want to make is this image here. I had a lot of fun looking at this image. Dave sent this around earlier today. He even, only just a few hours ago, even made it better. And Dave, when I saw the improved imaging based off the comments that you received, I couldn't, I couldn't not show this image. This is, I really like this one. As what I see when I see this image is I could almost feel a name come for it. It's the not nebula nebulas. There's two main targets inside this image, the ring nebula towards the top right, and then another galaxy in the top left. I haven't written it down. It's IC 1296, and both these are given. This is what's called the planetary nebula in the bottom right, and spoiler, it has nothing to do with planets. And then top left, around 100 years ago, this was what was called a spiral nebula. You could still call it that, but we've moved past that. And around 100 years ago, if you can believe it or not, and I like this, I even had a hard time believing it myself, but 100 years ago, there was something called the Great Debate in astronomy, and it was between Heber Curtis and Harlow Shapley. A very famous debate in which they were arguing about what they called these spiral nebulae, right? And so the things that look like this target in the top left, they're roughly the same size as other nebulae that we might have seen, this planetary nebula and the Horsehead Nebula and all these other nebulas. And so they said, but it's got this weird spiral structure, and these are starting to pop up a lot. We should probably talk about what these are. And in one camp, they were saying, okay, these are just they're just that. They're a nebula, gas and dust, and they're within our own galaxy. Maybe maybe these are early forming solar systems, they might have thought, and that each of these arms would eventually conjure into a planet itself. And the other argument was, no, it's actually even a more radical argument that ended up being the correct one, is no, this is not the same nebula. It's not nearby this one at all. This is actually, this could be, it's a billion times bigger and 100,000 times farther away. And not only that, but we live in one of those, and at the time they really thought that the Milky Way was the extent of the universe. Only 100 years ago, we were convinced there was one galaxy, that was the universe. And the argument was, no, we are one of many, many, many galaxies. And every single time we see one of these spiral nebulae, those are other galaxies just like ours that we live in, other universes. Complete paradigm shift. And we look back on that and say, oh man, it should have been obvious. But no, it wasn't. If this image makes it not obvious, they look to be the same size, both diffuse objects, but one is actually a billion times bigger, but 100,000 times farther away. So that's a galaxy. We're going to look at some more galaxies. And in the bottom right, this is the Ring Nebula. And this is what happened. What we're seeing when we look at the Ring Nebula. It's called a planetary nebula. Nothing to do with planets, but it's really the remnant of a dying star, a sun-like star. And when stars come towards the end of their lifetimes, when they run out of fuel, when they run out of hydrogen, they leave the main sequence. If they're heavy enough, they'll be able to have enough energy to begin to fuse helium, called the helium flash. You work your way up the alpha chain, going up the periodic table in steps of 2. You might be able to fuse carbon or oxygen up to that. But eventually, you'll run out of energy, and you'll no longer be able to fuse, and you'll run out of fuel. And depending on your mass, you might have a few different grand finales. But a sun-like star like this one goes through, once it starts running out of fuel, its last breath, it starts to ebb and flow and release shells of gas in what are called nova. And this ring nebula, these are the shells that it was expelling as it came to the end of its life. And what remains in the center is a white dwarf, the remnant core of that star, held together by what's called electron degeneracy pressure, which you're welcome to ask about, but I don't know if we want to go into right now. And that core is going to simply cool. It's going to remain as it is. It no longer can fuse, and it's going to continue to cool for billions and billions of years until the end of time, really. And it'll become dimmer and dimmer. And it's called a white dwarf star. And so it's amazing that Dave was able to capture both the ring, the dwarf star itself, and a companion galaxy to compare to. And so I really loved the contrast there, and I thought it was a nice caveat. So it's the nebulas that are not nebulas. We used to throw the term nebula at just about anything that was extended that wasn't a star, or a star or a comet. That's a nebula. And so now we're breaking down into much. We're in just 100 years, we've built on so much. It's really incredible.
Dave, how did you get that? Was it a filter that you used to get the colors?
Yeah, they were just normal red, green, and blue filters.
Okay.
Yeah. There was nothing special. I was going to retake that with some special filters that zero in on the elements that compose those gas shells, as Scott said. And I haven't done so yet, but when I will, I'll share it with you, with everyone, whoever's interested.
Do we know why the outer edge is red and the inner areas are bluer?
Yeah, it's basically different gases. So there's a halo, and the red is mainly hydrogen, and then you walk in from there, and the next gas is nitrogen, and the bluey, and that's kind of a white color. And then you go in from that, and that bluey color is oxygen. And I think in the middle, closest to the star, I think now is mainly helium. And there's a great, if you look up this nebula, the Ring Nebula, and if you Google it, they'll take you to a NASA site, which shows you in 3 dimensions. They've modeled how this looks and why it appears like a ring. And there's various shapes these can take, but they're generally colorful and interesting. And so,
yeah, absolutely. There's lots of planetary nebula out there that are asymmetric or have multiple different rings off center from the white dwarf itself. And it's all the complex physics that goes through. There's magnetic fields of the star, the rotation of the star. If there's a companion, if it's a binary star, all of these things can contribute to the shape of the nebula that you'll eventually see.
So yeah, that star in the middle is actually giving off UV light, which you can't see. And the camera doesn't capture, filters that out. And what that UV light is then bouncing off these various molecules or the various atoms, and those atoms emit their own, so they absorb the UV photons and then give off their own photons. And the photons they give off are a characteristic color of that element.
That's absolutely right. I agree. Anyways, that was my small caveat about the not nebulas. Although you'll even notice that that last little bit, the last explanation that Dave gave, is actually very similar in physics as to what's going on in the Horsehead and Flame Nebula. Hot stars, this is a dwarf star, the remnant of a star, but hot stars giving off UV, high energy, ionizing radiation, exciting other gases and molecules that give off characteristic wavelengths or characteristic colors. And so in that sense, yes, I guess it is a nebula. And even with when we go back to the spiral nebulas, galaxies, a little bit silly to think of them as nebulas, but every star in that galaxy, this is a spiral galaxy, so this would be considered a star-forming galaxy still. It's no longer, it's not passive. So it's going to be filled to the brim with star-forming regions, just like the Horsehead Nebula and the Flame Nebula and the Orion Molecular Gas Cloud Complex. That's what a galaxy is. And so what we'll build towards is why I start with that beginning. That's the ground zero, is all of these star forming regions. And by building those up, you can build all the way to galaxies. And so in some sense, this is just one big conglomeration of nebula. So it is kind of a nebula. So that's kind of where the confusion came from. But the not nebulas, I call it. There you go. But what I wanted to do is we started at ground zero, and I wanted to take us on a journey through, kind of accumulating more like building blocks all the way up to galaxies, which I enjoy the most. And so the next stop on our journey is after a star forming region. After we consider stars that are formed, it forms stars, and we're building the constituents of star clusters. And star clusters are the constituents or the building blocks of galaxies, and galaxies are the building blocks to galaxy clusters, the cosmic web itself, and our universe as a whole. And so while a star forming region like the Orion molecular cloud complex, all those different star forming nebula, while that tends to form open clusters within the spiral arms or the disk of a spiral galaxy, this is not an open cluster. This is a globular cluster. So I really love this image. So this is it's the Hercules cluster, or M13 globular cluster, taken by Brock. And maybe Brock, if you want to give a few comments on that. But I'll just say that I want to sort out the confusion, is that the nebula, like the first one we showed, will not make globular clusters. The formation of globular clusters is a little bit, they're all really, really old. All the globular clusters that we see, they are almost like ancient artifacts. When you study globular clusters, you are studying the earliest formation of the galaxy itself. And rather than being distributed through the disk of the galaxy, you see them in what's called the halo, in a sphere around the galaxy. And they're intrinsically important to both the galaxy's formation, its history, and by studying the globular clusters, you can actually infer details about the history of the galaxy itself. And we'll start there. Brock, do you have anything to say about taking this image?
Well, I guess one interesting point is that there's actually a galaxy in this image, if you look carefully to the lower left.
This one here?
Yeah, I don't know which galaxy, if it even has a number.
I found it. I found it online. It was IC 4617, edge-on spiral galaxy there.
This picture was taken just a couple of weeks ago.
Yeah.
Really, really, really nice, clear night that we had.
Yeah.
Really good seeing, just fluked.
And so a globular cluster like the one Brock has just taken just a few days ago, this is made up of hundreds of thousands of stars. He's been able to resolve all the way down into the densest part of the cluster. And you'll be able to notice that the cluster itself, it's densest in the center, and then slowly diffuses towards its edges in characteristic ways. Arguably almost Gaussian. But this is a gravitationally bound, very early, made very early in the Milky Way. So the Milky Way, as James was saying, is around 10 billion years old. These globular clusters, you can analyze the stellar populations, what's left behind. And these are upwards of 10 billion years old. This was made at the same time as the Milky Way, or potentially even earlier. And by studying how many globular clusters the Milky Way has, there's about 150 known globular clusters in what's called the halo around the Milky Way. That's, when you're talking astronomy, 150 is not a lot. That's not a huge number. So there's not very many of these, and these are really when you study these, you're studying the origins of the chemistry of our galaxy, the star formation history, potential interactions. Globular clusters can be stripped by tidal and by gravitational poles of nearby high mass galaxies, and so very, very important building block towards galaxies. With that in mind, let's get to where I really want to go, where I tend to be most excited. Here's another image from Brock. Let me get rid of this circle I drew. This is what's called the pinwheel galaxy. Many galaxies claim to be the pinwheel galaxy. It's a bit of an easy name to throw around at face-on spirals, right? But you can absolutely find this as M101, so the 101st entry in the Messier catalog. And why I wanted to go to this one next is, first of all, it's you start to begin to see on our journey. We're in our galaxy portion of our journey, and you can really start to see face-on spirals are a great way to gauge the details, the ongoing of what's happening inside of a galaxy. And so you have the central bulge, which hosts the supermassive black hole in its center. And then you see, spiral arms that go around. And the spiral arms, they're not they're not smooth. They're kind of lumpy, and they have I guess you guys can see my cursor, or I hope you can. There's just kind of clumps of bright lights in Brock's image here. And why is that? What you're seeing is active star formation. These are the nebula, the complex molecular clouds where stars are being formed that we showed at the very beginning. And it starts to piece together. What else can I say about? Oh, here we go. I guess I could say more about what a galaxy should look like, but I'm going to get to the juicy stuff. You might notice if you step back, maybe squint your eyes a little bit, think really hard, you might see it's not symmetrical. It's not a perfect pinwheel. Why is that? Well, I was thinking to myself, I go, okay, it hasn't been colossally disrupted. It just seems to be a little bit more diffuse on one side, and one arm seems to be kind of pulled away on the opposite side. And you can even see in Brock's imaging here the faint arm that's been extended with some ongoing, maybe even sparked star formation in that arm. And it's asymmetrical, not because it's undergone a merger, but because it's undergone a recent a near pass with another massive galaxy. And what happens is these are called, they're tidal features, or the gravity as these two massive behemoths go by each other. And it's just enough to kind of strip away, maybe pull away that one spiral that was once much tighter in as the other arms are, and even maybe even push away some of the gas and the molecular clouds and diffuse them. And what happens during close encounters, we call them, or in the pair phase of a merger process, is that close encounter, that jerk, that quick, hundreds of millions of years sometimes, can be enough to trigger those gas clouds that may have found a nice equilibrium. All of a sudden, you've got another galaxy come by, and it just shakes it up. And that can be enough to take gas clouds that were once in a nice equilibrium and then start to shrink down, collapse, get disrupted, and more stars begin to form. So this galaxy would have what I would call an enhanced star formation rate, as it is in a pair phase that may one day merge, depending on the kinematics of the system.
Scott?
Yes.
If this happened to our galaxy,
yes,
would we feel anything?
Absolutely not. Absolutely not.
Okay.
The claim is that when Andromeda in 4 billion years or whatever, Andromeda and the Milky Way are on a collision course, that we'll barely even feel that. And that's going to be a colossal merger event. Whereas this was just kind of a near, they just kind of skimmed each other. So this is even more gradual, a little bit gentler. And so you can see that by and large, very little has changed in this one. And I'll actually add that you could actually argue we're undergoing something similar at present. We're basically in the process of accreting or merging with smaller dwarf galaxies. And people have studied this. The ones that I'm most in tune with, I think I saw Sarah Klapoff join this Zoom call. I don't know if I'm supposed to give shout outs, but Sorry, Sarah, if you didn't want that. But she's working with Karun Thanjavur. Oh, I'm doing more shout outs. And something that they're doing is actually studying the remainder, the star streams that remain from recent mergers with our galaxy. So we're in a constant state of having things crash into us, but we really don't notice. When it's minor, as things are like this, over many millions of years, it's quite gradual and we don't really notice.
The Large Magellanic Cloud is doing that to us now too, right?
Yeah, so that's up next, basically.
Oh.
Yeah. They would be there. I believe they're on they will be soon accreted. So merging in some sense, but they do they do a dance. They'll do a nice, over hundreds of millions of years, they'll dance around the Milky Way and likely eventually accrete and become part of the Milky Way.
Brock, how long did it take to take this photo?
I think it was one night, probably an entire night. So probably, I think 4 hours of exposure. It's actually quite a faint object. It's it's much more faint than a lot of the other ones.
Mm-hmm. Thanks.
And while we're on it, I'll also just show, I think Dave has one as well. A little bit of a different angle from it, and a little bit rotated. But this is also Dave's image as well. This seems to be a it's hard to say whether this is a dwarf galaxy that's orbiting the Pinwheel Galaxy, or if it's what we would call an extended, or it was some sort of star-forming region that was once a part of a tidal arm that got ripped away due to some gravity. But it looks like it could be something, could be the Pinwheel Galaxy's version of like a Large Magellanic Cloud, for example. Just a nearby dwarf galaxy. But great imaging from these two guys. Where to next?
Got just a quick question about the asymmetry and this type of galaxy. Would you say that perhaps the forces that are acting on these galaxies are maybe sporadic and they come in kind of hiccups, and that explains some of the asymmetry? Yeah,
absolutely. So I'll add that a lot of my work has been trying to find asymmetric galaxies. We simply do measurements of asymmetry by taking an image and rotating it 180 degrees and subtracting those two images. That's our definition of asymmetry. You can sum that up and it'll give you a value. And you can normalize it between 0 and 1, so on and so forth. And what you'll find is that for pairs, my work is mostly with recent mergers, post mergers in some form, but oftentimes there's a pair phase. I would argue this is it's in a pair phase with, I'm not sure. So it's another fairly massive galaxy. It was around 300 to 400 million years ago. NGC 5474 came through against the grain and kind of pulled out that tidal arm. But what'll eventually happen is they're probably bound to each other now. If you're close enough to gravitationally affect a galaxy this much, you might have done something like this, crossed paths, and then a billion years later, that's relatively short in galaxy evolution timescales. Billion years later, it'll come back and maybe do it again. And the second time around, it'll become even more asymmetric. At its farthest point, this might actually go back. This asymmetric features might actually return to normal because it wasn't that disruptive of an event. But when that galaxy comes back around a second time, it's going to be closer. It's going to be more bound, and so it's going to do more damage. And it'll continue this dance, and it'll become faster and faster until it just becomes a full chaotic mess and becomes an elliptical galaxy. That's what we can't watch that unfold. That's a 1 to 2, like that's a multi-billion year process. So we can't, as people who have been, we didn't know there was more than one galaxy in the universe 100 years ago. So we can't watch a multi-billion year event unfold, but we've simulated them. And we can see that you can calculate the distance between them and that asymmetry parameter. And the asymmetry will actually do bumps as it comes through. So it'll spike, and then it might settle back down again. And it'll spike and it'll settle back down again. Until it'll spike the most when the full merger happens, and then it'll settle down to almost zero as a spheroidal galaxy. And so then that's its final state. But it could, again, merge with another galaxy later on.
That's great. Thank you.
Of course. Okay, I'll do, we're running a little low on time, so we're not going to get to all galaxies, but there's a few that we could maybe look at, just to kind of give you a flavor of the different types of morphologies, shapes of galaxies that are out there. And of course, I'm very attached to unique morphology of galaxies and galaxy morphology in general. That's my field of study. Here's this is what's called Bode's galaxy, named after Johann Bode, who discovered it on New Year's Eve in 1774, long ago. Probably claimed it was a spiral nebula. Didn't know what it was. And this one is unique as it has very close-in spirals, but then two big arms that extend outwards. It's star-forming. It has an AGN, so it has an active galactic nucleus. It's much redder towards the center, so it has older stellar population in the center, but it's still star-forming towards the edges, indicative of perhaps recent, maybe accumulation of dwarf galaxies or so on. No major merger has happened in this galaxy's lifetime. Yeah, a little bit of kind of added flavor there. This galaxy is, again, these are 12 million light years away. It's relatively, it's Milky Way sized-ish at around 90 kilolight years across, maybe a bit bigger. But size of galaxies is all wishy-washy anyways. These galaxies are, most of their mass is actually bundled up in dark matter, so it extends way out in a sphere beyond this anyways. We just can't see it. Yeah, Brock, do you have anything to say about capturing Bode's galaxy?
No, not much. I mean, it's using my big Celestron Cassegrain. It would have been, again, on a single night.
Right.
Probably the better part of a night, lots of exposures.
Right.
I don't have the details in front of me. I should have, but
no worries. What else can we look at? I was talking a lot about that pair phase. While I'm talking about the pair phase, it might be a good idea to look at the Whirlpool galaxy. This is a very common galaxy to be imaged. Both Brock and Dave have one in their portfolios, and this is a spectacular, relatively nearby galaxy interaction, commonly mistaken for ongoing merger. But this galaxy, so it's clearly a beautiful spiral galaxy, but with a something going on the right hand side here. What the heck is that? Over the past hundreds of millions of years, this galaxy is actually passing behind it, on the far side of us and this galaxy. And so this would be in a late stage of pair phase. And you can see that, you can imagine this galaxy may have passed once already, long ago. It might have disrupted the spiral arms and it went back to normal. But now as it passes behind, you're seeing the same thing again. The spiral arm on the far side is extended out and becoming blurry. And this one is almost being pulled towards the galaxy itself, creating asymmetric features that we'll be able to measure. And this is a popular target just because it's extremely interesting. They're super close together on sky, but they're farther apart than you might think. And lots of physics and interactions going on in this image. And it's face on and nearby. So there's been recent studies, a couple apods, or I guess for this one, only one astronomy picture of the day. But recently they went through and they measured the magnetic field within the spiral arms. And you can actually see that on the side where the galaxy is kind of closer, the magnetic fields all start getting jumbled up. And so now this provides an opportunity to understand what happens to the magnetic field structure within galaxies as they are in their pair phase and will eventually merge with a companion galaxy, so on and so forth. Any other thoughts on or questions about the whirlpool here?
How do they measure the magnetic fields?
Oh,
How do they visualize that?
Absolutely. So they have no, that's nothing to do with the magnetic. Here we go. Hidden magnetic chaos. So what they do is they you can actually measure. Here we go. An intrinsic. So what happens is the magnetic fields will align. So some polar molecules will align with the magnetic field and then emit polarized radiation.
Okay.
And that polarization is actually 90 degrees to the magnetic field. So they measure with a polarimeter, which I have also studied. We built one at UVic and wrote a paper on. So you can measure the direction of wiggliness, the polarization of the light emitting from these particles. And then you basically rotate that by 90 degrees and you can infer the direction of the magnetic field.
Mm-hmm.
And the only caveat I'll add to this is I read the paper on this and I have no idea where they got such a beautiful image from. Because the actual resolution of the magnetic field data that they had was not as fine-grained detailed. They definitely took some artistic leisure.
I think Brock must have taken that one because I don't remember taking it.
But anyways, what I was saying is you can see kind of in the spiral arms towards the interior, they're kind of, the magnetic field is along the spiral arms, as is we've seen typical for them. But then towards the outskirts where the merger's happening, or I guess close interaction, it just becomes chaotic. There's no longer, so that's what I was saying there. Okay, and we're coming close to the top of the hour. So the final location of where we'll end our night, I'd love to end with the Virgo cluster. So this is a nearby galaxy cluster. So the same way nebula and star clusters are the constituents of galaxies. Galaxies become the constituents, the building blocks for star cluster or galaxy clusters. And galaxy clusters, especially the Virgo cluster, I think is the nearest. Might be beaten by Fornax, but the Fornax galaxy cluster. But the Virgo cluster is nearby galaxy cluster with, depending on, back to the question, how many stars can you see in the night sky? It depends. Well, depending on how you classify a galaxy, what brightness it is, how massive it has to be, there's anywhere of up to around 2,000 members of this galaxy cluster, 2,000 galaxies, all gravitationally bound to each other, making up the heart of what's called the Virgo supercluster, to which we belong. a cluster of galaxy clusters, the heart of the cosmic, a heart of the cosmic web that is really the structure of our universe. And so what galaxy clusters allow is all of these galaxies are evolving right before our eyes, and they're all coming together, gravitationally interacting with each other. They're being stripped. You can see these two galaxies here that are called colloquially the eyes of the Virgo cluster. It's in this image, it doesn't show up, but they both kind of almost appear to have eyelids if you look in some of the other closer images. But the diversity of galaxies, you have edge-on disks, you have face-on spirals, you have massive elliptical galaxies. I believe this one here is M87. And before I make any more guesses, I love this other piece that Dave went through all the trouble to go through and highlight all the targets or the galaxies he could find. But there's even more hidden away, faint dwarf galaxies that you won't be able to see. And of course, you used NGC. That's fair. But I believe this would be M87, the home of Poveghi, the first ever imaged black hole that came out a few years ago. So this is what I worked on this cluster. I was doing the evolution of dwarf galaxies in this cluster, and we considered in our paper, we're basically considering, and what's common to do, we consider M87 to be the heart, the gravitational center of the cluster, and it really dictates the gravitational ongoings of the cluster. And as such, it's accreting dwarf galaxies, it's accreting mate, it's always undergoing, it's already the result of probably hundreds of mergers. And as such, gas is being funneled onto its black hole. That black hole then exudes high energy beams, which can be imaged. And that's what's called an active galactic nuclei. And it allowed us to study and image the first ever black hole. But a lot of amazing ongoings and a lot of studies. And it was a pleasure to be a part of. Here's a face-on spiral galaxy, probably undergoing a merger. Some really amazing things to see. What else can I say about this? The last thing I'll add, if I can tie it all together, is globular clusters, which we showed Brock's M13 earlier in the night, are extremely important to studying the Virgo galaxy cluster. Each galaxy in this galaxy cluster has a certain number of globular clusters around it. Those globular clusters tell you a lot about its star formation history, its interaction history. And you can actually count the number of globular clusters around each galaxy and relative to their distance from M87. And you find that they actually have an enhancement in the number of globular clusters towards the center as they had more intense star formation histories as they fell into the cluster. That was the result that prompted my research last summer. And you found that galaxies towards the center of the cluster had older stellar populations. They evolved earlier in their life cycle and went quiescent. They stopped forming stars. So basically what happens is as dwarf galaxies fall into the cluster, they are disrupted. They undergo a spike in star formation and then use up all of that gas clouds such that they can no longer form stars, and then become quiescent galaxies towards their center. And so it all ties together. And this is really just another building block in what's the cosmic web and the universe as a whole. And it's 11:04, so I'll stop talking. And thanks everyone for their attention. If you have any questions.
Scott.
Yeah, thank you. Thank you. And actually, just before I say anything, kudos to the three of you for bringing this wonderful blend of aesthetics and science. I really love how that came together. And Scott, we haven't seen the last of you. I'm gonna definitely try to get you back for a reprise so that we can learn a little bit more about the architecture of the universe. Wonderful. Thank you very much.
My pleasure. Thank you.
Thanks, Scott.
Thank you.
Do we have any time for quick questions, Lori? Or
I mean, it's after 11. I think
Okay.
I think maybe we better, unless if people want to stick around for a minute or two, but I think we need to let people go. Thanks to everybody that's been online today, to Reg and to Scott, Dave and Brock and David, and Patricia, who was on the telephone because she didn't have her internet ready to do the program, but we'll do that again later. To Aaron, who also will do some work for the eclipse a little bit later on, and thanks to everybody else that kind of came on to have a look. Great program, and I learned a lot. I've got all kinds of notes here that I'm going to have to take to pull it all together. So again, thank you for being part of the FDAO star parties, and we hope to see you again on June the 26th. And then we have another 2 in July, and another 2 in August. So we've still got the summer to go. And then, oh my goodness, James isn't on anymore, but I sure hope that we might be open up at the center maybe in the fall. So let's just cross fingers and see whether or not we might actually be up there for some time in the fall. So, all right. So Calvin, you can count us out and count us off. Thanks to everybody else for being online, and we'll see you again in a couple of weeks. Okay, thanks
to
everyone.
Everyone watching on YouTube.
On
and
YouTube,
on
yeah,
Zoom.
terrific. Yeah.
Staying up late with us.
Yeah. Thanks everybody.
Good night, everybody.
Good night.